All right, all right. Hello, everyone. Good morning. Good morning. Let me let me put on the blinds. There you go. That's way better. Hope everyone's doing well. Whoosh. Ouch! I trapped my finger between my chair and the desk. That is not good. Hello, hello, hello. Hope you guys are doing well. Bamberg, hi. How tall are you? I don't know. I haven't measured myself in like quite a while. Um, I'm like 176 centimeters last time I checked. I'm not sure how much that is in inches, but yeah, for American standards, it's like pretty average. For Colombian standards, I don't consider tall. It depends on what part of the world you go to. For the Netherlands, I am extremely small, you know. But yeah, I think it's like 176 centimeters. I don't remember. Anyways, um, yeah, a centimeter max. That's true. That's true. It's what I'm used to, right? Um, but yeah, I hope everyone is doing well. Um, so as you guys know already, we've been reading The Joy of Cryptography, and today we're going to be taking a look at the Columbia Max. Hopefully, because I like Columbia a lot. So Columbia Maxing is definitely one of the things that must be done. But either way. Um, so today we're gonna continue and we're going to start reading about key exchange, about public key cryptography. Okay. Um, you're gonna do something hard today. What are you gonna do? Thinking without Claude. Let's go. Anyways, but yeah. So remember, these first sort of streams related to the new project are going to be very. There's gonna be no coding. Right? We're gonna be reading. SS Ripple. Hello. Welcome to the stream. So yeah, as I was explaining, these first few sessions are not going to involve any coding, which I know may be boring for some of you, but they are needed, right? We're going to be reading cryptography so that we sort of understand underlying concepts. I do not think these are strictly needed for blockchain, right? In the sense that there is no sort of how could I? You could just understand the cryptography concepts that you need in like 20 minutes, but we want to understand everything from the ground up, quite literally, including the cryptography part. So we're reading everything about it, we're understanding, and etc. So these first sessions, once again, maybe have me in the background, maybe, read along. You're free to do whatever you want, but just know there are going to be a lot of reading. And today is a lot of reading. Each chapter takes around 2 hours to complete, and we have to complete 4 chapters. This is like 8 hours minimum of reading. So prepare yourselves, okay? Because we're transitioning to the reading scene. Okay? So this is going to be basically like an audiobook. Okay. So chapter 13, public key cryptography, and we're going to have the key exchange. All security guarantees of symmetric key cryptography stem from the basic assumption that the sender and the receiver know a secret key that the adversary doesn't. It's finally time to face the obvious follow-up question. Where does the secret key come from? This chapter is about how two users who have no shared secrets can obtain a shared secret even in the presence of an eavesdropper. 13.1 Cyclic groups. Let's go. Now we're starting with the actual math. This chapter builds towards a key exchange protocol based in an algebraic structure called a cyclic group. The concept is best illustrated by an example involving multiplication modulo a prime. The following Sage code prints the powers of 2 mod 13. So we have, this guy Sage, right? Notice that every number from 1 through 12 appears above. In other words, every element of 1 through 12 can be written as a power of 2 mod 13. Perfect. This example shows that 2 is a special element mod 13. Other elements are not so special. So as you can see here, well, not every element of 1 through 12 can be written as a power of 3. Right? If we are to use multiplication as our operation, then we get 139. We don't get through the full 1 through 12. Definition of cyclic groups. So this is, the usual definition for groups. If you've taken a math class, this should be natural. A set G is called a group if it has an. I see a message in the chat. Give me a second. I'll start reading this section, and then once I finish, we'll read. So I'll read the chat between sections so that we can have like cohesive ideas. But don't worry, I'll get there eventually. Definition 13.1.3 of cyclic groups. A set G is called a group if it has an operation defined on its elements, which we will write as multiplication that satisfies the following rules. So we have closure, right? For any two elements in the group, their product also stays in the group. Identity, that is, there is some identity element such that identity times anything is that thing, independent of the order. Associativity is just the usual property of associativity, and inverses, right? For any element of the group, there is some element such that this happens. The order of a group is its cardinality, the usual definition, and the group is called a cyclic group if there is a special element G called a generator, such that this happens, right? Such that every element can be generated by the generator, right? There's not, that is, every element of G can be written as a power of G. But this is a different G. In these expressions, G to the I means this. Generators of cyclic groups are also sometimes called primitive roots. The set 1 through 12 is a group whose operation is multiplication mod 13. Recall from section 3.4 that since 13 is prime, every element in the set has a multiplicative inverse. Furthermore, this group is cyclic, with 2 as a generator. This group has order 12. Perfect. A cyclic group can have more than one generator. See if you can find another generator of 1 through 12. We have multiplicative groups. If n is prime, then the set z sub n asterisk is called the multiplicative group mod n. Is a cyclic group with respect to multiplication mod n. Perfect. Multiplicative groups modulo a prime are a good mental model of cyclic groups. However, there are much better choices of cyclic groups for cryptography, which we will see later. Therefore, the results in this chapter are presented abstractly in terms of an unspecified cyclic group. Okay, we finished that section. So let's see. We have SS Ripple. What do you think of the job market? Is it difficult to find a job as a Swede? Not sure. Not sure because I do have to say I've been currently trying to apply to internships because I'm going to be a master's student next year and have already gotten rejections. So it's kind of funny. Rudy Fan says, hi. Hello, Rudy Fan. Andrew, I wrote a program to find generators of a group when reading this. Yeah, pretty good. Let's see. But yeah, this is the usual of groups. Oh my god, is this that language? Yuiwa? Brother. Oh no, dude, I knew it. I knew it, bro. Brother. 2, 6, 7, and 11. I imagine it's like if I change this number to what could we put in here? Maybe 11. I see. What's another round number? 19. Then, pretty good. Yeah, not sure about good being the whatever this thing is on. So modulo values call a function but keep its first argument before its outputs. Power raise a value to a power, make an array of all natural numbers less than a number, brother. Anyways, let's continue reading before Andrew makes us go insane. Sadly, yeah. Anyways, if G is cyclic with order n, then its elements can be written as this, all right? Which makes sense, right? Where G is a generator, if the generator can generate all of the elements of the group, then all of the elements of the group can be written in this way. Thus, one way to sample uniformly from G is to first sample an exponent A uniformly from sub n and output G to the A. Makes sense, right? Exponents in the group work mod n. In other words, we have this. Finding a generator, right? To do cryptography in a cyclic group, you need to know a generator of the group. A generator can be found by trial and error. If you know if you know the prime factorization of the group's order, we won't prove the following fundamental fact about groups. Let G be an element, not necessarily a generator, of a group G, and define the order of G as the smallest positive integer k such that G to the k is equal to 1. Then for any G belonging to G, the order of G divides the order of the group G. Yeah, this is I always confuse. Oh yeah, this is Lagrange's theorem. Just using the fact that this load has a subgroup. Is a cyclic subgroup, then you use Lagrange's, and you get that it divides. Yeah, perfect. Ganga Kamal, hello. I'm seeing you've started something new. Missed yesterday's streams. Yes, yes. As the title says, we are coding a blockchain from scratch in Rust. Um, Nonetheless, there is some preliminary knowledge, and as I was mentioning, like the amount of cryptography we need to know in order to understand the original Bitcoin paper is, I would say, not that much, right? You just need to understand what asymmetric cryptography is, at least from a landscape level, and then we'll be fine. But we want to understand it really well, so we're just, we're reading. We're reading about cryptography with this resource that Andrew shared with us, Joy of Cryptography, that has been extremely, extremely helpful. Sharif, good afternoon. Hello, Itachi. How are you? I hope you guys are fine. But yeah, so now we're reading about. Oh, this is Lagrange's theorem, right? Yeah. Okay. I was like, wait, you use Lagrange's and stuff, and then like, this is literally Lagrange's theorem. If I remember correctly, the proof for Lagrange's theorem was you first. Well, it's basically proving that every single, all cosets have the same cardinality, and then you find some trivial. Well, I wouldn't say true. Well, it is kind of trivial. Some trivial transformation that allows you to a bijection between the cosets. And that way you can say everything is partitioned by these cosets by the same amount, and thus it must be that they divide the order of the group. But yeah, anyways. Another way to define the order of G is the cardinality of the set this, right? If G is a generator, then its order is exactly cardinality of G. In a previous example, we showed that with respect to arithmetic mod 13, G equals 3 has order 3, which indeed divides the order of the group Z sub 13 asterisk, right? So multiplicative Z 13. Now, suppose we want to check whether G is a generator of this guy. In other words, we want to check whether G has order n. We simply need to check whether G to the k is equal to 1 for any proper divisor k of n. Okay? So raise G to the power of n over q for every prime divisor q of n. And if none of these exponentiations result in 1, then G must have order n and be a generator. Which makes sense, right? So if every single subgroup divides the order of the group, more specifically, if the cyclic group generated by a single element is, divides the order of that little group, divides the order of the big group, then it means that you only have to only have to go through the divisors of the big group until you find a 1. Yeah, if you don't find a 1, then it means that the order of your group has to be equal to the order of the big group, and then you're fine. Right? Yeah. Makes sense. Simply need to check this. Okay. Pablo Soter. Hi, how's it going? Did you finish the allocator? Yes, we finished the allocator, actually, which was very, very nice. We benchmark it. It went face to face with Malloc, which is great. It means we, at least we did something that's decently efficient, that's decently good. I'll be working on it, behind the scenes, just because, we wanted to transition to something different. Now we are working on creating a blockchain from scratch. We're doing it in Rust because, we want to learn Rust. But before all of that, we are sort of learning all of the preliminaries. Right. So, yeah. Thank you for hanging around. And Itachi, I see you're fine. That's good to know. But, yeah, so let's see. We simply need to check whether g to the k equals 1 for any proper divisor k of n. Yes. Right. This makes sense because it's like quite literally, right, the order of your group is a divisor of n. So if you check it for every single divisor of n, then you're gonna know. So raise g to the power of n over q for every prime divisor q of n. If none of these exponentiations result in 1, then g must have order n and be a generator. So understand this part. Let me see. Why is it that it's enough to raise g to the power of n over q for every prime divisor q of n? Which I feel a little embarrassed by, right? I'm a math major, blah blah blah, but I'm a little bit rusty on this. I just need like a few seconds to think. G to the power n over q for every prime divisor q of n. Okay, makes sense. Makes sense. I would say, right? Because suppose the order of your group, the order of little g, right? Suppose the order of little g is a divisor. So okay, let me say it this way. When we raise g to the power of n over q, right? Why n over q? It's a good question because here it's saying, well, this makes sense. This makes a lot of intuitive sense, no? We know the order of little g must divide the order of the big group. So if we just check every divisor and we raise it to that power, then, we would be going through all the possible orders, right? And in that sense, if we find out 1, then it means that the order of g, this guy, is going to be smaller than the actual group. And so this is not a generator. So it's only when we've checked all of the divisors that we actually know, yes, the order of this guy is actually the whole group. Now, why is it sufficient? So we would have to go through all of the divisors, but they are telling us, actually, it's enough to just raise it to the power of n over q for every prime divisor q of n, right? So why is that the case? Why is it enough? Well, you can imagine, I think Excalibur would come in handy here. You can imagine that, imagine listing off all of the divisors of n. So in this case, rather than, having these guys, let me erase all of this. In the meantime, Pablo Soter, a blockchain is completely out of my knowledge, but curious about how you code it. Exactly. It's one of the reasons why we chose it, right? It's like out of the ordinary path. We have no idea how to code it. Compared to maybe other things related to operating systems and stuff where you actually kind of have an idea or is a very common path. So we just said, all right, let's code a blockchain because we don't know how it works, right? So I think a good example could be with 24, right? So imagine 24. What are the divisors of 24? Well, it would be 1, 2, 3. I'm sorry, not 3, not 3 and 2. I just started listing random numbers. No, 3 is the divisor. Oh my God. Okay, 1, 2, 3, 4, 6, 8, 12, and 24 itself, right? We got this, right? These are all of the divisors, right? 1 and 24, 2 and 12, 3 and 18, 4 and 6. Yes. Okay, perfect. So you can imagine that here we're saying, okay, check G to the K for where K is a divisor and do it for every single divisor, right? So then we're like one, dun, 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 dun. But now they're telling us, well, it's just enough to check 24 divided by the prime divisor. So the prime divisors would be this guy and this guy. Why? Well, because you can imagine every divisor, right? If you take its prime decomposition, so for example here, 2 times 2 times 3, right? If you grab 24, it's going to be 2 times 2 times 2 times 3, right? When you're dividing by a prime divisor, what you're doing is effectively taking out one of these prime factors, which is the sort of minimal operation you can do to end up with a divisor. So it gives you a divisor that's just one prime divisor away, and thus that divisor is going to contain sort of a section of the previous ones. It is a little bit. I'm not sure how to explain myself, but suppose you test 12, right? Which would be removed from 24 at 2. Notice that 12, right, contains within itself or has as divisors 6, 4, 3, 2, and 1, right? Because it's just like you just remove a single prime factor. So a lot of the numbers that are divisors are contained within these other prime factors. What it means is that if you test 12, you're also going to be able to test all of the divisors that divide 12. And now if you, instead of this 2, had removed the 3, then you test 8, which is the last one, right? So it's like if you just use another Q, then you're gonna be able to test all of them. That was the worst explanation I've ever been given. Uh, I've woken up and like I'm a little fried today, but yeah. So yo, can you kill time while I wait for it to be time to leave for gospel? Is that it over there? Fire's gone, damn, missed. Brother, what? What are you shooting, bro? But good. Thank you for hanging around. No. Yeah. Um, let's see. So now, suppose we're going to check. Okay, we see this. The discrete logarithm problem. Since every element in a cyclic group can be written as some power of the generator, a natural question is, given an element of the group, which power of the generator is it? The discrete logarithm problem in a cyclic group G is precisely that, right? Given an element A of the group and a generator G, find an integer A such that A is equal to G to the A. This problem is called a logarithm problem because it involves solving for the unknown exponent in an expression like A equals G to the A. But discrete logarithms are different from usual logarithms in a few important ways. The solution to a discrete logarithm problem is always an integer, hence the discrete part. And in some cyclic groups, the discrete logarithm problem is computationally hard. There is no known polynomial time algorithm. This second point is relevant to cryptography. It means that in some cyclic groups, the operation A and then raising it to the power of the generator is easy to compute, but its inverse is hard to compute. Well, that joke tanked, huh? Was using the kill time thing for the. Oh, brother. Brother. Okay. Sorry. Dude, you guys have no. I'm really bad when it comes to the written jokes. Like, they fly over my head. I'm not sure why. I'm really dense. Like, anyways, but yeah, let's see. Measuring efficiency. We need to be careful when talking about the efficiency of algorithms dealing with huge numbers. Consider the following algorithm for solving the discrete log problem in a cyclic group of order n. Right, so we get this algorithm where we have u is 1, and then for a equals 1 to n, we simply, we just go through every single power and then return, right? I previously claimed that there is no polynomial time algorithm for the discrete log, but isn't this an O of n time algorithm that works for any group? Indeed, this algorithm is O of n, but it is not the length of the algorithm's input. The algorithm receives just one group element as input, and if the group has order 2 to the k, each group element can be written in k bits. The running time of this elementary discrete log algorithm, as a function of its actual input length, which is k, is O of 2 to the k. It is not a polynomial time algorithm. As we'll see later in this chapter, cryptography based on cyclic groups requires groups where n is huge. Damn. So an algorithm running in OFN time is useless. When we say that the discrete logarithm problem is hard, we mean there is no known algorithm for discrete log that runs a polynomial time as a function of k in a group of order 2 to the k. Perfect. So what we're saying here is you get an element, right? In a given group, you can think of that element, well, or like we require the groups to be of order 2 to the k, or at least approaching that, where k would be the amount of bits you would need to pinpoint this element, or is like the way we think about it, and thus this thing is exponential. Perfect. Cyclic group strategy. So the defining property of a cyclic group is that every element can be written as g to the a. Given g to the a, it is hard to compute a, but while reasoning about cryptography, it usually makes things much easier if you express every group element in this way, as the power of the generator. For example, if some cryptographic algorithm receives the group element a and computes a to the b, it will probably aid your understanding of the algorithm to think about a as g to the a. For some a might be hard to compute, and a to the b as g to the ab. Yeah, perfect. So every element is a power of the generator, so sometimes it helps to think of it as precisely that. Efficient exponentiations. Let's see. Cryptography based on cyclic groups involves a lot of exponentiation, computing expressions like g to the a. This is meant to be the easy direction compared to the hard direction of computing discrete logarithms. So it's important to understand exactly how these expressions can be computed efficiently in polynomial time in the number of bits required to write each group element. For the sake of correctness, let's consider multiplicative groups modulo a prime and use the prime p equals 2 to the 130 minus 5 as an example. You can trust me that 2 is a generator of this group. How would you compute an expression like this guy, right? 2 to the ba 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 ba. Even Sage, which handles huge integers with ease, seems to have problems. We have an overflow in the MCZ type. Imagine, of course, right? Yeah, so you can find the factors of this guy. Actually, not the factors. You just find things that add up to this, split it into multiplications, modulo distributes across those, and then continue with your life? One went wrong. We have just asked H to first evaluate this as an integer and then reduce it mod p. But that huge integer would require 154 gigabytes to write down, which is beyond what Sage is willing to use. And this is with a small exponent, a 40-bit integer. Imagine if the exponent were 256 bits long. Concept 1, reduce as you go. The best trick for modular arithmetic is that if you need the final answer modulo p, then you can and should reduce all intermediate steps mod p. Yeah, makes sense. In other words, you can compute an expression like 2 to the blah 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 by performing many multiplications, and these should be multiplications mod p, not multiplications over the integers. Hopefully this makes sense, because after all, we're thinking of a cyclic group whose operation is multiplication mod p, not multiplication over the integers. Yeah. We can ask Sage to use multiplication mod p by creating a mod object which overloads multiplication, and therefore exponentiation appropriately. Okay. What? Sure. Concept two, exponentiation by squaring. Okay. Let me think about something. Yeah, okay. Your mental model for evaluating an expression like x to the b might be something like this. R is equal to 1, do b times r is equal to r times x, right? But this can't possibly be how Sage does it, because it can't compute this thing instantly, right? It could not have possibly performed these many multiplications. And indeed, this simple exponentiation algorithm runs in O of b time, which is exponential in the number of bits required to write b. A much better way to exponentiate can be illustrated with the following example. Yeah, exactly. So then you split them all together, you put to the powers, and then you distribute the modulo. Okay. Every dot or square of this expression represents one multiplication that must be performed. And you can see that this expression computes x to the 19 using not 18 multiplications, but only 6. Okay, pretty good. This exponentiation strategy is called repeated squaring and can be written recursively. Interesting. Remember, the multiplications and squarings in this algorithm should use the cyclic group operation so that intermediate values are consistently reduced modulo p. The total cost of this algorithm is O of log b multiplications, because at each recursive level, it performs the most 2 multiplications, then recurses on a new exponent roughly half the size, and then its running time is polynomial in the number of bits in b. Perfect. Penguin operator, welcome. Yay. We have a word of warning. Any implementation of this exponentiation algorithm on a real computer will almost surely leave side effects that leak information about the exponent. And when we use cyclic groups or cryptography, the exponent is usually the secret key. So you should never actually use this exponentiation algorithm for cryptography. See this exercise for an illustration of the problem, and see this exercise for a better alternative. Let's go. DP Hellman. Yay. Okay. We got to the goats. Okay. In 1978, Whitfield Diffie and Martin Hellman published New Directions in Cryptography, the most important paper in the history of cryptography. In this paper, they describe an ingenious method for two users to generate a shared secret key from nothing. The method is interactive. The two users, who share no secrets, exchange messages with each other until they can both compute a common key. Yet anyone observing their communication will not be able to learn this key. In their method, amazingly, you learn more by participating than by observing. The DP-Hellman protocol uses a cyclic group with generator G. The main idea is that the users exchange public messages A, G to the A and G to the B, and define G to the AB as their shared secret. The user who sent G to the A knows the secret A and can compute the key as this. The other user knows B and can compute the secret as this guy. The usual rules of exponents hold in any cyclic group. However, an outside observer who sees G to the A and G to the B will have difficulty computing G to the AB. Okay, this makes um, this makes sense, right? Alice doesn't really know what number Bob chose for the exponent, but she can just power that to the power of whatever she has in order to get the common key. An external observer, because of the, um, the discrete logarithm problem, will not be able to figure it out, just because it would be pretty difficult. They wouldn't be able to get whatever this guy is. So if they see both the GA and GB, they would be able to compute G to the A plus B because they could multiply both things. But there's really no way to obtain G of A times B. from the information that I mean, there is a way, of course, right? Brute forcing or maybe something else, but not a polynomial logarithm for it, algorithm for it. So the construction is this. Let G be a cyclic group with generator G and order n. The Diffie-Hellman key exchange, DHKE, protocol is defined as follows. So we have Alice chooses a random Z mod n number, and Bob chooses a random B Z mod n number. Right? They define these guys, they send it to each other, and then we define K to be equal to whatever B has, put it to the power of A, and then we output K. They'll end up with the same key. Everybody saw what happened, but nobody can deduce what the key is. Very interesting. Here's how to interpret a protocol diagram like this. It uses actions, I'll specify sequentially. Yeah, I mean, I feel the diagram is pretty intuitive, right? Example. Here is one possible execution of DHKE, use of Diffie-Hellman, using the multiplicative group over prime n equals 2 to the 130 minus 5 with generator 2. The order of the group is n minus 1. Here is the interaction from Alice's point of view. So, wow. She runs this, right? She gets n. She generates a random integer between 1 and n minus 1. Then she computes her element, right? A is equal to 2, which is a generator of the group, powers it to, its tutor, and then it powers it to whatever she has, right? Then she sends A to Bob and receives B from Bob, and she just simply, creates the exponentiation of B. Perfect. In layman's speak, each decides their own separate encryption and decryption keys, hand out the encryption key to the one that is to encrypt messages, and send them to them and decrypt said messages after they arrive. So each encrypts messages meant for the other to decrypt with the key the other provided. Yeah, right, but this would be after, this would be a use of Diffie-Hellman. Diffie-Hellman is just describing the way in which the keys can be exchanged. But yeah, that is, I think, going to be just the gist of it at the end, right? Perfect. From Bob's point of view, it's going to be this. In this example, both Alice and Bob compute the same key. These are large numbers for humans, but they are still too small to provide good security. See below. So I enter the passive security section. So to keep things simple, in this chapter we focus on the most basic security property of a key exchange protocol, security against a completely passive eavesdropper. An adversary who merely observes the victim's interaction should not be able to learn their shared key. More precisely, the victim's shared key should look pseudo-random from the adversary's point of view. Yeah. The security condition can be formalized by saying that the following two libraries are indistinguishable. So obtaining two numbers, okay, this is the real one, return G to the A, G to the B, and G to the AB, and then returning this much. Okay, perfect. In other words, no adversary should be able to distinguish the real key from a truly uniform, unrelated key, even after seeing the Diffie-Hellman transcript. Remember, in a real application of Diffie-Hellman, the users will use the resultant shared key for symmetric key cryptography. But in this attack scenario, the libraries give the key to the adversary. This is a way of saying the Diffie-Hellman shared key is just as good as a truly uniform key, no matter what it is used for. Given the earlier contents of this chapter, you might be expected proof of how Diffie-Hellman is secure in this sense, assuming that the discrete logarithm problem is hard in the cyclic group G. Unfortunately, no such proof is known. Instead, the Diffie-Hellman protocol is so fundamental that we simply treat its passive security as a fundamental assumption about cyclic groups and give it a nice name. Interesting. Right, decisional Diffie-Hellman assumption, let G be a discrete group with order n and generator G. The decisional Diffie-Hellman assumption in G is that the libraries, these two, are indistinguishable. Okay, such a fundamental thing at the heart of cryptography, and we just leave it as a given. Very interesting. The DDH assumption is equivalent to the statement that the Diffie-Hellman protocol is passively secure. It is a useful assumption which can be used to prove the security of many other more complicated constructions. There's a disclaimer. Key exchange, as defined in this chapter, is unauthenticated. Passive security means that two protocol participants, whoever they may be, agree on a key that looks pseudo-random to an eavesdropper. Passive security gives no guarantees about the identity of those participants. In the real world, there is rarely much use in agreeing on a key shared with whoever might be on the other end of this connection. Usually one has a clear intent about the KE partner's identity. Think of this chapter not as the complete story of key exchange, but just the beginning. What we're calling passive security is the bare minimum level of protection you might want to the key exchange protocol. Incorporating authentication into key exchange is the subject of chapter 18. Interesting. All right. How do we choose the strong cycle group? Right. Although we have built intuition about cyclic groups using multiplicative groups Z and star, these are not the best choice for Diffie-Hellman for a few reasons. The most glaring one is that DDH is false in this guy, right? There is an efficient algorithm that, given G to the A inside Z and star, can determine whether A is even or odd. And this is enough to contradict the DDH assumption. Ooh, what? Interesting. There is an efficient algorithm that, given G to the A, can determine whether A is even or odd, which is enough to contradict the DDH assumption. Interesting. So we have quadratic residues. The problem with Z and star has something to do with the fact that it has n minus 1 elements. N minus 1 elements, which is even when n is not prime. If we want the DDH assumption to hold in a cyclic group, it is helpful if the group's order does not have small prime factors, like 2 in this case. One way to eliminate this factor of 2 is to consider the subgroup of quadratic residues, mod n. The group of quadratic residues modulo n, written QR and star, is the set of all squares and z sub n. Wait. Graphs. Oh, okay, yeah, this is completely different. Okay, sure. I was like, whoa, this is a flashback. Something I've heard before. Anyways, in particular, when z sub n star is cyclic, right, QRN star consists of all the elements of Zn star with even exponents. Thus, QRN is also cyclic with G square as its generator, which makes sense, right? When n is an odd prime, squaring mod n is a 2-to-1 function. Yes, just like it is in the real numbers. Thus, QRN star contains exactly half of the elements of Zn star. So n minus 1 over 2. The best chance to ensure problems like DDH and discrete logarithm are hard is when n minus 1 over 2 is itself a prime. If n and n minus 1 over 2 are both prime, then n is called a safe prime. The DDH assumption is widely believed to hold in the group of quadratic residues QRN modulo a safe prime. All right. Let's see. Rather than use just one prime factor, why not multiple? Makes getting back to the originals harder if the key handed out is the result of multiple prime factors. So what do you mean by that? When you say, so you're saying rather than use just one prime factor, right? Where? You said use one prime factor. What do you mean by use one prime factor? Makes getting back to the originals harder if the key handed out is a result of multiple prime factors. Yeah. What do you mean by this? So where do you say we should use multiple prime factors and why? But yeah, I'll continue reading. I'll take a look at the. I'll be attentive to the chat once the answer is there. But Yeah, let's see. Um, Easy to get the prime factor of 7 times 7 than this. Yes, yes. Look, I right, but like, where do you want to implement this? Like, where do you say we need this? Right, it is my question. Because currently we haven't been involved with, picking two prime factors. We've only grabbed one prime, and that is for the order of the group so far. Um, the other ones have been random. So yeah, let me know. Avoid DDH altogether. So exercise 13.8 proposes another way around the deficiencies of the ZN star. It is possible to prove security of a modified variant of Diffie-Hellman under a slightly weaker assumption about the cyclic group. Although DDH does not hold in ZN star, this weaker assumption is widely believed to hold. It's so funny. It's widely believed to hold. It was just a question. Maybe I'm looking at something spoken of later without knowing I am. Oh yeah, I'm not sure. That's why I'm asking, like, which part are you talking about? Um we should be using more prime factors because we have been only using a single prime factor. Not prime factor, sorry, a single prime, right? The single prime is the order of the group, right? We just say we have to have an order of a group that is prime, and then we generate, well, not the order, the n, because then the order of the group is going to be n minus 1, but, right, understandable. Um, so yeah, that's the only prime we've picked. Then we pick a random number, uh, we pick another random number, right? And so on. But yeah, so I'm not sure what. Sorry, the order of the group. It's never said to be. Yeah, let's see. Mm, Suji, are you saying factorization is harder the more prime factors there are? Maybe that's what Suji is saying? I'm not sure. Nazwe, what do you think about making a game engine in C using OpenGL Vulkan from scratch as the next project on stream? It could be interesting. I do have to say, I'm not very interested in game engines currently. So it would be a little bit difficult to convince me of doing that, especially like I've heard that Vulkan is very verbose, and I think a game engine does require like a lot of time and a lot of thought put into it. Um, yeah. So I'm not sure. I'm not sure. I don't think it would be the next project. It could be one in the future, but not in the near future. Yeah. Um, I would expect so. I mean, getting square root takes longer than the square, so why not getting multiple factors be harder than a single factor? Hello, Coding Barra. Yo, ho, ho, ho. Coding Barra. Say hello to Coding Barra. And yeah, let's see. So I guess your question refers more to this part. Where is it? It's where we divide by Q and the order of the group. Here. To raise G to the power of n over Q for every prime divisor Q of n. If none of these exponentiations result in 1, then G must have order n and be a generator. So in this case, it is helpful to find all of the prime factors of n, and it's precisely what makes the problem difficult. So I think you maybe do you know you can rate people too, even though you're not affiliate? Yeah. Like I've tried rating people in the past, like live, right? Live showing you guys how I try to do it, but it just doesn't work. So I'll try today again. We've tried like 3 times, and then it says the person doesn't have their things set up correctly. And so it's like, it's a little sad and kind of annoying on Twitch's side because I'm like, dude, please let me rate people. But yeah. Yeah. No, go to the VODs. If you take a look at the VODs at the end of some streams, I've been like slash raid Christopher T, slash raid DeFerrari, slash raid, and then it just wouldn't let me. It's just unfortunate. But yeah. Um, Problem is, the more factors there are, the smaller factors will be. This makes them easier to find with brute force. If you find any of them, you can just divide number by its factor, and problem becomes much easier for all next factors. There you go. Great explication on Andrew's side. But yeah, so sorry, I've been getting lost on this. Where are we here? Yes, okay. Elliptic curves, the best cyclic groups with Diffie-Hellman, are not based on multiplication mod n, but on an entirely different algebraic structure called an elliptic curve. These groups are introduced in more detail in section 13.4. Let's see. So, wait. Sweetie, for huge numbers, it doesn't matter how many factors you have. It only matters what factors you use. Like Andrew Kroski said, don't use small factors. How so? To identify even one, you have to identify all at once to produce the encryption key, and in turn know the decryption key by what you found. Also, I wasn't saying use small factors, they're just easier for typing. Wait, give me a second. How so? To identify even one, you have to identify all at once. Not really, right? Because you have a number, right? You have n. You just have to find a single prime factor to make the problem easier, right? So you give you like, I don't know, 36, right? You're gonna start with 1, then you look at 2, and then you're like, oh, 2 is a prime factor, right? Notice that we haven't yet found the remaining prime factors, but we found 2. We know 2 is 1. And so now we can make the problem easier. How? Well, you grab 2, right? Now then you know this prime factor. And then you say, well, the remaining prime factors have to be in what results from 36 divided by 2, which would be 23. And so now, sorry, not 23. Oh my God. 13, right? 13. No, I said 36 or 26? Brother. That's a stupid 18 if I said 36. Right? So now the number is 18. Now it's like a way smaller number. So let's try again. 1 and 2, right? Oh, I found 2, which is a prime factor of 18. Well, right, now the problem is easier, plus the fact that 18 had 2 as a prime factor made it really easy for me to just brute force it. That gives us 9 after that. And so now the problem comes from 36, trying to find some prime factor for 36, to trying to find some prime factor for 9. Right? The problem decreases in difficulty as you go through the prime factors. So if you have many prime factors, it's very likely that, or it's more likely to find smaller prime factors because, the more of them you have, right? And yeah, it's also going to be easier to find them by brute force, as Andrew was saying. So it's desirable to have the least amount of them, or perhaps there is a specific sweet spot, right, where the number is really huge, but then the amount of prime factors is despite not being only 2, still considerably difficult to find. So yeah, I'd say that would be the reason, right? My prime factor is 12. Nobody expects 12. All right, buddy. Also, for the multi-factor thing, don't have to use just prime factors. Could also use normal numbers to make the problem harder. So what do you mean by this? Because the problem is that in the end, right, if you use normal numbers, right, normal numbers can be, are built up by primes. So by adding a normal number, you would just be adding a bunch of primes still. So in the end, thinking of the problem as just using primes is equivalent, because say I say, oh yeah, grab this number and then multiply it by 6, right? What would I be doing? Well, I'd be multiplying yes by 6, but if you find the prime decomposition of that, it would be 2 times 3. So, oh, multiply this by 2 times 3. So now you've added 2 and 3 as prime factors, which is really bad, right? Or multiply this by 10,540,665. Then you wouldn't be adding, you would be multiplying by that number, but remember the prime decomposition of that number has primes within it, most remarkably 5, right? So, boom, right? And then you put that in. Who says you have to multiply only? So if that's the case, right? What would you suggest? You would suggest like adding normal numbers. In that case, you would ruin the entire group structure, right? Potentially, all right, because n is a prime number for a reason, because the z's of n star is going to be a well-behaved, cyclic group. Which I mean, every single one of them would be, but yeah. So if you just you have your prime number and then you add 3 to it, the whole group structure could potentially be ruined. Maybe you get lucky and get like one less than another prime, but that would be impossible to guarantee, right? If I'm understanding correctly. Right. So one issue with crypto stuff is that some things which look like it makes it more secure do actually the opposite. Yeah, that makes sense. So, but I think it is worth thinking about what Suiji is saying. Often primes are only 2 across from the last prime. Just add 2 to your main prime and multiply the result against the original prime to get a larger number to work with. Wait. Often primes are only 2 across from the last prime. Just add 2 to your main prime and multiply the result against the original prime to get a larger number to work with. That becomes an issue, right? Well, first of all, right, you wouldn't know, like that wouldn't be guaranteed, right? Maybe you grab a prime and then you add 2 to it, then you don't know whether or not you've landed on another prime. Maybe you can check that. Maybe you can be like, okay, yeah, right, let's do that. But either way, it's right. It's not. We how do I say this? Like, we only need a single prime for the order of the group, right? So what you're suggesting is like generate a big number, right? But here we're not trying to generate a big number, right? Here we only need a single prime, and then we need to find its factors. So we don't have a power over like generating stuff, generating a composite number. That, at least up until this point, has not been something useful. Probably will in the future, not sure. But we've only needed a single prime, and then we need to find its prime factors. So it's like we're already given what we need to find. Like, we're already given this prime. The problem is find its prime factors, and that becomes a very difficult problem. About the topic of choosing bad factors to make it insecure, here Tom is making HTTP as insecure as possible for his website using this math tricks. Pretty funny video. Let me see. Let me. Right, what is this video? Let's see. No one can force me to have a secure website. Bro, what is this? Full heartbleed support. Man in the mirror. Man in the mirror attack. Dude, these puns are great. Brother. Oh, sorry, wait. I think my internet is like very... Right, Tom I'll follow this guy. Wait, we should watch this video some other time. It's 35 minutes, and my internet is very laggy. But yeah, it's a good video to watch. Uh, I'll see if I can watch it at some point in time. But yeah. So, anyways. But yeah. But yeah, you forget n does not need to be a prime. Only the factors need to be a prime. Um, we read right multiplicative groups. If n is a prime, then the set Zn star called the multiplicative group modulo n is a cyclic group with respect to multiplication mod n. So we do need it for the multiplicative groups, right? Maybe you mean something else? Do you mean the quadratic residue? But in that case, you still need a baseline multiplicative group, right? And so you still need n to be prime. See? Let's see, maybe choosing a strong cycle group. Although we have built intuition about cycle groups using multiplicative groups, which would require n to be prime, these are not the best choice for Diffie-Hellman for a few reasons. The most glaring one is that DDH's falls in Zn star. There is an efficient algorithm that given g to the a belonging to here can determine whether a is even or odd, and this is enough to contradict the DDH assumption. The exercises explore this fact in more depth. We have quadratic residues. The problem with Zn star has something to do with the fact that it has n minus 1 elements, which is even when n is an odd prime. If we want the DDH assumption to hold in a cyclic group, it is helpful if the group's order does not have small prime factors, like 2 in this case. One way to eliminate this factor of 2 is to consider the subgroup of quadratic residues mod n. Okay, the group of quadratic residues modulo n, written as this, is the set of all squares in Zn star. Particular when Zn star is cyclic, QRN star consists of all the elements of Zn star with even exponents. Thus, this guy is cyclic, with G2 as its generator. When n is not prime, squaring mod n is a 2-to-1 function, just like it is in the real numbers. Thus, QRN star contains exactly half of the elements of Zn star, so n minus 1 over 2. The best chance to ensure problems like DDH and discrete logarithm are hard is when n minus 1 over 2 is itself a prime. If n and n minus 1 over 2 are both prime, then n is called a safe prime. The DDH assumption is widely believed to hold in the group of quadratic residues QRN star modulo a safe prime. So we need a prime number, it seems. Then here we have, the exercise and then elliptic curves. Key exchange in the abstract. Okay, so this is where we stopped. Tom Seven is awesome. Recommend every video of him. I did not know about this guy. That seems like such a fun channel. Anyways, and if factors are big enough, then even if they work out 2 is being added before I multiply against the original, they still need to work out p to make use of that. N is the public encryption key, correct? The decryption key is the factors, correct? Then it does not matter. Wait, no, right? So there is. I don't think there is a decryption. Okay, let me read this carefully. Maybe I'm misunderstanding. N is the public encryption key. No. Or like, are you calling big N? Because there's two N's. There's little n and there's big N, right? Little n is the order of the cyclic group you're considering. No, it's not the order. It's the prime from which you extract the order by subtracting 1. Right, it's the guy from which Zn star, right? The public encryption key would be whatever, like, right? There is, like, the encryption key is not public yet, right? Unless you mean G to the A, which is whatever Alice sends and whatever Bob sends. Yeah, because the key is never revealed itself, because then it would be a useless key. I imagine maybe you're referring to a different concept in cryptography, which uses all of these things, or maybe I'm misunderstanding. Let me guys know in the chat. Um, let's see. Uh, is the public encryption key correct? Right. So Alice chooses G to the A. Bob chooses G to the B. They multiplied on their own. The key is never revealed. Right. If you mean public encryption key by G to the A and G to the B respectively, the decryption key is the factors, correct? Not not really. What do you mean decryption key? Because they just exchanged a key, right? Uh if you're gonna use symmetric cryptography, then the key is gonna be the same as the encryption key. Uh yeah. I'm not sure. Maybe you're referring to RSA, which would be like different, right? I don't remember RSA, so I cannot tell you if it's exactly what you're talking about. But feel you have. I feel maybe what you say applies to later sections, maybe not this concept. I'm a little confused. But that's no security. The attacker can easily derive P plus 2 from P. I didn't say that was the only manipulation you could do. It's just an easy example to type. As much as I like to continue arguing my point, I need to leave now or I'll be late for gospel. Laters, gators. Oh yeah. Bye bye. Bye bye, Zwigi. But yeah. So let me guess, maybe I'm misunderstanding Zwigi's point. I don't see how it would make it more secure, and I think actually it would destroy the, like, the key assumptions we have, right? Little n being prime is necessary to get the multiplicative group to be a well-formed cyclic group, and so on. I think what he's referring to is RSA. I'm not completely sure, but I think. All right. Key exchange in the abstract. So the Diffie-Hellman protocol is just one example of a key exchange protocol. In this section, we formalize, let's see, the factors themselves are neither part of the private nor the public key. Yeah, exactly, right? Like, you just get the key, it's symmetric cryptography, so it's going to be the same key for both encryption and decryption. Well, I mean, you could use the key for whatever you want, right? But like, the only type of cryptography we've known so far is symmetric key cryptography, where they both share the same key. So you just use it for that, right? You are a participant, so you are supposed to know the key. The factors would only be needed if you're like an attacker, right? And you actually need to figure out what the key is. Yeah, right. So, and adding to and modifying the number doesn't make the problem finding factors inherently more difficult. In fact, it could make it even, less secure, because then you end up with numbers that perhaps don't have the properties that you would need. So yeah, anyways, let me know, guys, if I ever say something like completely mistaken, but I think that is the case, right? The Diffie-Hellman protocol is just one example of a key exchange protocol. In this section, we formalize key exchange as an abstract cryptographic primitive. Key exchange is more cumbersome to formalize than other primitives because it is inherently interactive. The security guarantee for key exchange involves two users interacting, and we need to be able to reason about the messages they exchange as well as the final output. Below is one possible approach for formalizing arbitrary interactive protocols. A two-party protocol consists of two programs, P1 and P2, containing special send and receive commands, which we write, right? We write this to denote the result of running P1 and P2 in the natural way. Whenever P1 executes send X, the value X is passed to the next RESP command in P2, and vice versa. The output of this is a triple, where T is the protocol's transcript, a sequence of all messages sent between P1 and P2 during the execution. Y1 is the final output of P1, and Y2 is the final output of P2. Perfect, sure. Example, Diffie-Hellman as an abstract protocol. Right. The Diffie-Hellman protocol can be expressed as the following pair of programs, Alice and Bob. Then it returns A, B, the transcript. Then Alice's output and then Bob's output, which is also A to the B, right? Definition, the abstract key exchange, which is correct as in security. Let P1, P2 be a two-party protocol where both users output a value from K. Then P1, P2 is a key exchange protocol if the two parties terminate with matching outputs. More formally, the following code outputs true with probability 1. Okay, yeah, decent. The protocol satisfies passive security if the following two libraries are indistinguishable. Perfect. Okay, so the real one would be, you execute the program and then you have this. And random would be the operations are performed, but then you just grab a random key. Okay. Key exchange is also commonly called key agreement. I like to think of LKRAND as describing a world in which Alice and Bob run a key exchange protocol as a decoy, but then a magical fairy gives them both an unrelated key, K prime, that they use for their symmetric key cryptography. Remember, this is a definition of passive security against an adversary who merely observes the victim's interaction. It applies no guarantees for the victim when an adversary participates in the protocol and possibly deviates from the specification. It provides no guarantees about the identities of the key exchange participants. Chapter 18 is devoted to these security properties. So we can imagine, I imagine this passive security being highlighted is very important because if we are to imagine an eavesdropper, right, that actually has some sort of action on the channel, they would be able to say, receive Alice's initial thing, G to the A. They would intercept that message. They would choose their own little, element of the group, just as Bob does, and send that to Alice before Bob gets to send something. Alice is fooled, and then, so it's important to remark this passive security thing. Yeah, it would just be a man in the middle, right? You could also, as a man in the middle, allow communication between Alice and Bob without the need to, right? Intercept, you just need to, well, actually, no, you need to intercept the messages, put your own thing in, then send it back to Alice. So a man in the middle attack would work here because if you raise it to the power of whatever you chose, then you have power over everything, right? So is that true? I just want to make sure that's true. What I'm saying makes sense, because if not, then I'm not understanding. So we have Alice, we have Bob, they're communicating with each other, right? Alice sends G to the A to Bob, Bob sends G to the B to Alice, and the way they discover their key is A already knows what little a is, and B knows what little b is. They just raise each to the power of whatever they have, whatever they received, and they have exchanged the key. So I imagine that if you have E, which would be Eve, what it could do is it could say, well, let me intercept first Alice's message, which would be the G to the A. They raise that to the power of E, and then they send that to Bob. Bob will eventually send G to the B. Eve raises that to the power of E2, right? EB, and then sends it to Alice. Alice will get G to the, right, this message, raised to the power of A, so ABE, and Bob will get this thing raised to the power of that, which would be GABE, but does Eve get to know the secret key? The answer is no. And so Eve, from the perspective of this, if it were to do it this way, it wouldn't be, they wouldn't be able to know it. So it seems like the main way to do it would be just to intercept the channel and just, supplant B's identity. Just like cut communications with this guy and redirect the flow of traffic to E, right? Or make E respond faster than B. Because it seems like even if Eve, okay, I'm pretty sure there has to be a way, right? And I don't think if Eve, for man in the middle attacks, you need to read chapter and signing. Okay, that makes sense. We're just trying to see or to predict, okay, how would you do it, right? How would you do it with Diffie-Hellman if you were to be able to act on the information, you know? Because there is a huge emphasis on, remember, this is a passive thing, right? With this thing, it's not possible, right? Like we're seeing that Eve wouldn't be able to do it unless they like make a cut communication with B and somehow fool them to interact with Eve or something like that. But that would be of no use. Mm, you can't. Okay, okay. But then if you can't, right, why is there such an emphasis on if you have no shared secrets beforehand, there is no way to know who you're talking to. Oh, you mean of resolving identities? Yes, yes. The resolving identities, of course, right? You wouldn't be able to know. There has to be some way where you can resolve identities, and that's going to be explained later. I'm saying if two things, like if two parties, A and B, are performing Diffie-Hellman, right? And you as an eavesdropper are not only allowed to spy on them, but to modify or interact with the protocol itself, how would you steal the key? Right? That's what we're trying to resolve. Because they're saying, oh yeah, this works for a passive attacker. That is, they don't interact with the protocol. Now we're saying, okay, there is an emphasis they're putting there, which means that if you're not a passive attacker, there is a way to attack this. What is that way? That's what we're trying to reason through. Or do they mean like, oh, if you just fool Alice, then of course you're gonna be able to talk to her, right? Because if you fool Alice, right, then you establish Diffie-Hellman here, and then you establish Diffie-Hellman here, like completely independent Diffie-Hellmans. And then if you manage to fool both of them, Alice is gonna think they're sending a message to Bob, but they actually send it to you. You get that key, whatever, and then you just send it to Bob or something like that. Yeah, I don't know. Right? G to the A. You get G to the A E over here. And then that's what you send to Bob. Bob sends you G to the B. Right. Yeah, it's not clear to me how you would attack this. Because okay. I mean, right, this is the only way I can think of. Where you just have independent Diffie-Hellman, right? You establish this Diffie-Hellman with between A and E, and then just decrypt A's messages, um yeah, right? This would be like the only way. No. Where you know the key between A and yourself and B and yourself. They would be different keys, but you're in the middle, so you would be able to decrypt whatever comes here and then re-encrypt with this key and so on. Yeah, I think that's the only reasonable way you could do it. You cannot get them to agree on the same key, and you also have knowledge of that key. You can just fool them into thinking, yeah, you have to decrypt and re-encrypt. Yeah, okay. So that is the only way, right? There is no way to get them to agree on a single key, and then you also know what that key is. You always have to have two different keys. Right? Because you don't know the secret that A holds. You don't know the secret that B holds. And thus we're left, dumbfounded. Okay, sure. Perfect. Elliptic curves. Okay, this is a star chapter, but let's read it anyways. In section 13.2, we discussed QR star as a group in which the DDH assumption is believed to hold when P is a safe prime. However, that discussion has conveniently ignored the question of how big P should be. This is a question about concrete security. We typically choose parameters so that the best known attacks require 2 to the lambda effort. For example, the best known attacks against PRFs are simple brute force. So we can choose lambda bit PRFs, which I imagine is a pseudo-random function. Yeah. Keys, da da da. The best known attack against collision resistance is a birthday attack, which is faster than brute force. So we choose hash functions whose output length is 2 lambda. The best known way to break DDH in QRP is to solve the discrete logarithm problem of P. The best known discrete log algorithms are not polynomial time, but considerably faster than brute force. Here's a table showing for a few target values lambda how large P must be so that the fastest known discrete log algorithms require 2 to the lambda effort. Oh, wow. Dang, that's like huge. That's humongous. So 128. Right, if you want to require 2 to the lambda effort, then you have, damn, this one. In other words, Diffie-Hellman over QRP star requires group elements that are at least 3072 bits long. Wow. Since the cost of modular exponentiation algorithms scale with the cube of the input size, these huge groups are an expensive choice. This section is a brief overview of a completely different kind of cyclic group called an elliptic curve group, right, which disappointingly has very little to do with ellipses. These groups lack much of the structure of ZP star and QRP star, which is a good thing, since that additional structure is precisely what can make the discrete logarithm problem easier. The best known discrete log algorithms on elliptic curve groups require time 2 to the k over 2 in a group of order 2 to the k. Thus, we can make the discrete log problem require 2 to the lambda effort by choosing an elliptic curve group with order only 2 to the 2 lambda. Concretely, elliptic curves allow us to use Diffie-Hellman with 256-bit group elements instead of 3072-bit group elements. Wow, that's like pretty interesting. What's going on? What's happening with that? Elliptic curves over the real numbers. We will first build some geometric intuition for elliptic curves by investigating curves defined over the real numbers. Cryptographic applications use curves defined using modular arithmetic, which we will discuss later. Let let A and B be two fixed constants. The elliptic curve epsilon AB consists of all points x, y that satisfy the equation y squared equals x cubed plus ax plus b. Interesting. Below are a few representative shapes that an elliptic curve can take. Okay. Point addition. Given 2 points in an elliptic curve, there is a special way to add them, resulting in another point on the curve. This point addition operation is somewhat complicated, but it can be derived by understanding how straight lines intersect the elliptic curve. Okay, in direct definition. Given an elliptic curve, define an addition operation as follows. Include a special point at infinity, which lies on every vertical line. Think of it as both the north and south poles simultaneously. This point at infinity is considered to be an element of the elliptic curve, and it is called zero, since it is the addition operation's neutral element. If any line intersects the elliptic curve at 3 points A, B, and C, we say that A plus B plus C equals 0. The 3 points are counted with multiplicity, that is, we can have B is equal to C when the line is tangent to the curve. The 3 points may also include the point at infinity when the line is vertical. Okay, if any line intersects the elliptic curve at 3 points A, B, and C, we say that A plus B plus C equals 0. the 3 points are counted with multiplicity. Okay. So then in this way you define addition. Interesting, I guess. So then B plus C would be the additive inverse of A, right? Just by definition. Let's keep reading. Example 13.4. In each of the following pictures, the points A, B, and C sum to 0. Yes, this makes sort of sense, right? Okay. It's like x squared equals 0 has 1 root, but it has 2 roots if we count with multiplicity. Yeah, no, like I agree with the multiplicity, right? The multiplicity is not a problem. No, my problem is like the definition of addition, right? What is the motivation? Which I guess is what we're going to read. In the second picture, the line is tangent to the curve at b equals c. In the third picture, c is the point at infinity. Definition 13 might seem unsatisfying as a definition of an addition operation, but we can use it to define addition in a more concrete, procedural way. If A is a point on an elliptic curve, then minus A is the point obtained by reflecting A across the x-axis. The special point at infinity is its own reflection across the x-axis. Yeah, it's what we saw here, right? That makes total sense, right? Proof. Let B be the reflection of A across the x-axis. Then the line through A and B is vertical. Yeah, so it intersects the curve at the point at infinity. We might also have B equals A if the point is on the x-axis. Then the line we must consider is the tangent line at A, which, if it exists, will also be vertical because the curve is symmetric across the x-axis. This is the scenario illustrated in the third picture. Since A, B, and C are the intersection points between a line and a curve, we have this much. Yeah, makes sense. Since C is equal to 0, we then have A plus B is equal to 0. That would be, yeah, what we were saying, right? B plus C would be the inverse additive of A. The additive inverse, sorry, of A. Point addition can be performed procedurally in the following way. So observation 13. Let A and B be 2 points on an elliptic curve. To find A plus B, we imagine the line through A and B. If A is equal to B, then the line is tangent to the curve. If one of A and B is 0, the point at infinity, then the line is vertical. Denote by C the third intersection point of that line with the curve. Yes. So this makes total sense, right? Sure. Example 13.4.7. Each of the following pictures illustrates how to find A plus B given A and B. Okay. This, right. That definition, sure it is a definition. What is the motivation though? Additive notation for groups, right? These rules define an addition operation for points on an elliptic curve, and that operation satisfies the necessary rules for a mathematical group. Before now, we have written the operation of a cyclic group as multiplication, because this is just, again, right, this is just saying that this thing with plus is a group. But yeah. Expressions like g plus dynamo as written as 3g, yeah, so exponentiation becomes scalar multiplication when using additive notation. We generally write group elements in uppercase and scalars in lowercase in an attempt to reduce confusion. Keeping in mind that due to the the discrete logarithm problem in additive notation is the exact same thing just as in additive notation. If you want to become a cryptographer, it's imperative that you develop very passionate feelings about additive versus multiplicative notation. Yeah. Are we team additive or team multiplicative? That's a great question. What team are we on? I personally, I'm personally more like a multiplicative notation guy. I feel. I don't know about you guys. Let me know. But multiplicative notation makes a lot more sense, especially when you start to work with all the groups, right? It's also pretty similar to the symbol of function composition, which somehow makes it seem a little better to the mind. Like, what you're performing here is not necessarily a multiplication, it's like some sort of transformation. Anyways, elliptic curves modulo prime. Elliptic curves over the real numbers are helpful for developing a geometric intuition. But cryptography uses elliptic curves defined over the integers mod p, where p is a prime. Such curve consists of all points x, y, where the same equation is satisfied. Right. Group addition works by expressing the geometric steps from definition 13 algebraically and simply performing that algebraic manipulation mod p. Some of these steps, like finding the line passing through 2 points, require division, and thus p must be prime to ensure the existence of multiplicative inverses. Yeah, that makes total sense. Perfect. All right. Example 13.4.8. Most of the examples so far have used the curve this. Here are the points that satisfy this equation mod p equals 29. Point at infinity is not shown. Wow. So it almost seems rather random now, which is very interesting. Of course, the reflection across the x-axis is still present, it seems, yes, but it seems more scattered around. As you can see, geometric intuition is limited when working mod p, and it's best to rely on algebra alone. There are many choices for an elliptic curve. How should you choose one? The easy answer is to not choose your own, but to use a standard, vetted curve from a reputable library. The choices that motivate standard elliptic curves are beyond the scope of this short introduction. Okay, that's that. Example, curve 25,519. That's funny. It's like, it almost seems like the planets, right? Like in movies, right? Like, oh, we're on universe, the Spider-Man movies for Doctor Strange. We're on universe, and, this is Earth number 43, or, the Little Prince too, and his rose. We live in Comet, blah, 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 blah. Anyways, there's like curve 25,519. Yeah, interesting. Elliptic curves in Sage. Here's how you used Sage to list all points in the curve, for example. So it's like the only curve I heard anyone uses. I see, I see. So elliptic curve, this, elliptic curve defined by this much of a ring of integers modulo 29. Zmod 29 tells Sage to generate a curve with operations mod 29. The list -2, gives parameters of the curve equation. If you wonder why Sage prints the curve equation as this, when we asked for a coefficient of -2, it's because -2 is the same as 27. Yeah, okay. The dot points method will return all of the points on the curve, so don't do this for a curve with two. But if you print a point in the curve, it will display in a different coordinate system that we will not discuss. This alternate coordinate system avoids special cases to handle the point at infinity. These point objects can be converted to a more familiar x, y pair with the .xy method, which will raise an exception for the point at infinity since it has no xy coordinates. Interesting. To convert an xy pair to an elliptic curve point object, whose addition operation is overloaded properly, you can just use the elliptic curve object E as a constructor. Pitfalls in fine print. A complete treatment of elliptic curves is well beyond the scope of this book. To give you a peek into the guts of elliptic curves, here are a few issues that arise. Degenerate curves. The right-hand side of the elliptic curve equation is a cubic expression of x, and usually has 3 distinct roots. However, in this equation, then the cubic has repeated roots. We call the elliptic curve degenerate in this case. Degenerate curves have points with an undefined tangent, and the curve addition law breaks down for these points. Okay, so here we would have a problem. Here we would also have a problem. We always restrict our attention to A and B that avoids this degeneracy condition. So if curve equations, Point addition algorithm for elliptic curves involves many special cases, like when a is equal to b, when 1 of a comma b is the point at infinity, when a plus b is the point at infinity, and so on. These special cases can be tricky to implement correctly, and if one is not careful, the running time of the point addition algorithm may leak information about secret exponents. One way to improve the point addition algorithm is to use a different kind of defining equation for the curve. So far, we have considered only curves defined by this, known as a Weierstrass curve equation. All the curve equations are possibly notably Edwards curves, which are defined by this, interesting, or Montgomery curves, which are defined by by squared equals x cubed ax squared plus x. Interesting. Not every curve can be expressed by these special kinds of curve equation, but those that can enjoy improved point addition algorithms faster and with fewer special cases than Weierstrass curves. Okay. Twists. Let me read the chat. Let me guess. It's form of f comma y comma a, where x y is given by this, and a equals 0 is point at infinity. Andrew Krevsky, it's in form of this. Mario M, welcome back. Rudy Fund is the crypto expert. Yo. Alright. Rudy Fund just responded to Mario. It's pretty good. Alright. Twists. If x comma y is an elliptic curve, then so is x minus y. And these are the only two common points on the curve with this x coordinate. Thus, it is common to communicate points in the curve using only their x coordinate, plus one bit representing the sign of y. Interesting. However, not every x coordinate corresponds to a point in the curve. For example, in the elliptic curve y squared equals to over z29, there is no point with x coordinate 5, because the right-hand side of the curve equation evaluates to 3 mod 29, but there is no y satisfying y squared equals 3 mod 29. For every elliptic curve, there is a companion curve called the twist. Interestingly, every x coordinate corresponds to a point either on the primary curve or its twist, and never both. The two curves exactly partition the set of x coordinates. That's interesting. The twist of our example curve y squared has the form y squared equals c times the original equation, where c can be any non-square, say 3 in our example above. Twists can be problematic. Suppose a victim is running Diffie-Hellman, so they expect to receive an elliptic curve element and exponentiate it with the secret Diffie-Hellman exponent. Again, if group elements are communicated using only their x coordinates, and an adversary sends an x coordinate from the twist, then the victim will perform the exponentiation over the twist curve. It is possible that a discrete logarithm problem is much easier on the twist curve than on the primary curve, in which case this attack would make it easier for an adversary to recover the secret exponent. This problem can be dealt with in two ways. First, always check whether a point lies on the intended curve before performing operations on it. The second one is choose a cryptographically strong elliptic curve whose twist is also strong. Okay, we have cofactors and small subgroups. Many cryptographic applications of secret groups require a group of prime order. Unfortunately, elliptic curve groups often do not have prime order. For example, Edwards and Montgomery curve equations always produce a group whose order is a multiple 4. If we want to take advantage of the algorithmic benefits of those curve equations, we need a way to cope with their composite order. Below is a general discussion of composite order groups, which is not specific to elliptic curves. Therefore, we will use multiplicative notation. Suppose G is a cyclic group of composite order R times S with generator G. Thus, G is equal to G to the 0, blah, 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 blah. Yes, okay, order R times S, generator G, makes sense. And everything in the exponent happens mod RS. Now, consider the powers of GR. Yes, agree. There are only s possible values before completing a cycle. We say that GR generates a cyclic subgroup of order S. Yeah, that makes sense. The math of elliptic curves often gives us a cyclic group of order R times S, where R is very small and S is a huge prime. Usually R equals 4 or R equals 8. Oh, then it's going to be... Okay. This value is called the cofactor of the curve. Given such an elliptic curve, we can just take G to the R to be the generator, and everything will happen in the prime S order subgroup. Problem solved, right? Not so fast. Oh, that's exactly what I thought. Imagine a situation in which a victim receives a group element A from an untrusted source and computes A to the X, where X is the secret. X is secret. The computation A to the X will work fine, not just for elements of the prime order subgroup, but for the entire composite order group as well. In particular, an adversary could choose A from the order R subgroup. Okay, such a subgroup exists because R divides the overall order, yeah. The result of A to the X will wremain in the order R sub... Whoa. Such a subgroup exists because R divides the overall order. This is not necessarily true, right? You would need a little bit... I mean, if R is a prime, then sure, right? I think Cauchy's theorem gives you this. But it's not mentioned Cauchy's theorem anywhere. Anyways, okay, sure. The result of A to the X will remain in the order R subgroup. But because R is so small, it is easy to compute discrete logarithms in the order R subgroup by brute force. Thus, the adversary can compute the discrete log X modulo R, leaking some information about the secret X, which would not be possible if the computation remained in the desired order S subgroup. I see. Okay. These problems can be avoided by always ensuring that untrusted group elements are in the desired subgroup. The easiest way to do this is to raise an element to the R power. This is called clearing the cofactor. An alternative approach is proposed later in exercise 15.29. Oh, and then we have the exercises. Okay, give me 1 second. I'll be back. Hello. Yeah. We're back. We are so back. All right. So doing the exercises may take us, quite some time. Um, so yeah, I think we can continue to the next chapter. It was an entertaining read. Pretty good. And yeah, 2 hours basically. An hour and 50 minutes. Oof. Okay. That was a lot. I think we understood a little bit better, how everything works. Um, I hope we have Diffie-Hellman clear. It makes a lot of sense, right? So now we're going to go and transition to um, public key encryption. Ayush Sharma, what kind of web work you do? What do you mean web work? Yeah, let me know. What do you mean by web work? Um, and yeah, and then I'll answer the question. But in the meantime, let's go to the next chapter because we have a lot to read. Oh my god. Okay. Damn. I mean, website development. I don't do website development. Yeah, I don't. I mainly code like programs here, like say in C and C++. I haven't done web development in like years, many years. Maybe when I was in high school, I did like a couple websites, but completely forgot about this. Why do you have Firefox Dev Edition? I don't know. It's blue. Yeah, I feel it's a pretty solid reason. It's blue. So I like it more. And sometimes, if you want to know what a color is, you can just go to the little inspect and then grab the little guy here and then it'll tell you the color. I feel it's pretty neat. But yeah, that would be my honest answer. Uh yeah, I just like it more, right? But yeah, we have public key cryptography. So everybody, strap to your seats. Another article. Okay. So late in the game. What's the point? What do you mean? So late in the game, what's the point? By the way, CodeFlex32, welcome to the chat. Wait, what do you mean? So late in the game, what's the point? Do you mean like, oh, you joined the stream late, what are we doing? Let me know. Let me know, and then I'll answer. So let's see. Um, coding a blockchain from scratch, this late in the life of blockchain. Oh, I see. I'll answer that in a few seconds. First time chatter, we have Super Pichu26. Hello, welcome to chat. Hey, I found you by your memory allocator series recently on YouTube. It was a fun watch to learn about this stuff. Yo, let's go. But yeah, very. I hope you found it interesting, and I have yet to upload the last streams. We ended up finishing the memory allocator, right? So now the memory allocator is done, and you can see in the VODs the moment where we benchmark it and realize, oh yeah, it goes face to face with malloc. So that's pretty cool. And Ayush says crypto is done. Sure. Yeah. I mean, so the reason, and I've explained this quite sometimes, we just do this for the sake of learning, right? I feel like cryptocurrency, in perhaps the economical sense, the political sense, whatever, may not be the best of things, right? That is debatable, who knows? What I do know is it has a lot of components that are, from the engineering side, extremely interesting and clever. And it's the reason why we chose it as a project. We're going to build one from scratch, right? From scratch, quite literally from scratch. So no packages, no nothing. And yeah, we're going to do it to learn, right? So yeah, it combines a lot of stuff, right? Distributed systems, cryptography, it combines trust problems, proofs, etc., etc. So it is very interesting from that perspective. So yeah, in a symmetric, well, I mean, we continue with the next chapter, right? So you have public key encryption. In a symmetric key encryption scheme, both encryption and decryption use the same key. A public key scheme disrupts this idea and uses different keys for encryption and decryption. The encryption key, so this may be what Suiji was referring to, because what we previously were looking at had nothing to do with like an encryption key and a decryption key. We weren't even talking about encryption and decryption, right? We were talking just about the keys. But yeah, anyways, the encryption key can be made public so that anyone can send encrypted messages. The decryption key is kept private, and only the holder of this key can decrypt these messages. Ooh, exciting. Okay, security definitions for PKE, public key encryption. We start by introducing the syntax of a public key encryption scheme. Oh, sorry. In the public key setting, there is not one key but a key pair consisting of a private key and public key. These two keys must of course be correlated in some way. Therefore, a public key encryption scheme must include a separate key generation algorithm, keygen. Definition 14.1.1, syntax and correctness of public key encryption. A public key encryption scheme consists of the following algorithms. Keygen, which is a randomized algorithm that takes no inputs besides the security parameter, which we never write explicitly, and outputs a key pair, PK and SK, I imagine public key and secret key. Yeah, where P is the public key and SK is the private key. ENC is a randomized algorithm that takes a public key PK and plaintext M as input and returns a ciphertext C. DEC is a deterministic algorithm that takes a private key SK and a ciphertext C as input and returns a plaintext M, or raises an error. A PKE scheme is correct if the following program outputs true with probability 1 for all M in the message space. That makes sense, right? What does it mean for a key to be public? In the security definition, the library provides a way for the adversary calling program to learn it. By making this change to the security definitions for encryption and also ensuring that the correct key is used for encryption decryption, we obtain definitions of CPA and CCA security for PKE. So what is CPA? Chosen plaintext attack and chosen ciphertext attack. Okay. So definition 14.1.2, the chosen plaintext attack security for public key encryption, right? A PKE scheme sigma has security against chosen plaintext attacks if the following two libraries are indistinguishable. So we generate the key to ensure we're able to read the public key, but this is indistinguishable from picking a random ciphertext in the order of M. Okay, perfect. It's pretty good. You're a genius. You can't read those fancy symbols. Rotated M keygen. wait, what? Oh, rotated M keygen. True. This looks like Magneto's helmet. If you were to rotate it a little. Yeah. Anyways. Definition 14.1.3. We have the chosen ciphertext attacked. So a PKE scheme sigma has security against chosen ciphertext attacks if the following two libraries are indistinguishable. So now the problem is going to be, we generate the same thing, we are able to read the key. Encryption ends up being sampled from a random ciphertext in sigma. Then DC is defined as M. Oh, okay. So you just keep track of some sort of dictionary that tells you what the ciphertext is supposed to decode. Then it returns. And then on decryption of again C, we return this guy. If DC is defined, then return DC. Otherwise, return sigma. Okay, what is the purpose of this? Well, this is um the same. Let's see. I just can't read math symbols. I wish I could. Oh, I mean, yeah, this was called sigma, and that's all we need to know. It feels bad using LLMs to do math. That goes over my head. Yeah, I know. Like math is like actually insane. It's like really insane. Um, yeah. Yo, Andrew just did a cartwheel with the M. Let's go. Pretty good. Did you just say Sigma? Sigma man? Bro, what? Dude, yeah, I loaded this guy. Okay. Anyways. Sigma, Sigma male, Sigma male, Sigma male. It was Sigma boy, I know, but as in the CCA security definition for SKE, symmetric key encryption, ciphertext generated by CCA encoding are called challenge ciphertext. After seeing CPA and CCA security defined for PKE, you may also expect a definition of public key authenticated encryption. The spirit of AE is that no one can generate valid ciphertext. Okay. After seeing the banana, you may also expect a definition of public key authenticated encryption. The spirit of AE is that no one can generate valid ciphertexts except the person who holds the secret key. But the spirit of public key encryption is that anyone can encrypt ciphertexts. The two concepts are incompatible. So in the public key world, we will stop at CCA security. Okay. If anyone can encrypt, why can't I tell whether something is an encryption of M by re-encrypting M myself? This attack would work if PKE encryption were deterministic, but just like the case of SKE, public key encryption cannot be deterministic. It is tempting to think that encryption of PKM has no secrets because both of its arguments may be public. But the randomness that enc samples is a secret that the adversary doesn't know. The randomness used in an SKE's encoding algorithm is often included in its output, but this cannot be the case for a public key scheme. Okay, new chapter. Let's read the chat. If you just want to learn how they are pronounced, create an Anki deck for that and you'll learn. Oh, for the math symbols? I think whenever I go to the AI doctor, he will diagnose me with cluster. Very funny. The AI doctor. Anyways. Yeah, so we have one-time versus many-time encryption. Before describing an actual PKE scheme, let's first discuss a property of PKE that will make future security proofs easier. In the symmetric key world, it makes a difference whether a key is used to encrypt many plaintexts or just one. For example, OTP is secure when a key is used to encrypt one plaintext, but insecure when used for many encryptions. In the public key world, there is no such distinction. Any PKE scheme that is secure for a single encryption is also secure for many. What this means is that if we need to prove CPA security for a PKE scheme, it's enough to prove a simpler property of security for a single encryption. Oh, claim one-time CPA security for public key encryption. Let sigma be a PKE scheme. If the following two libraries are indistinguishable, then sigma has CPA security. Okay. So if C star is undefined, which we don't know, okay, C star is just the encryption between. Okay. What are we doing here? In these libraries, C star is static global and static slash global, and its value is fixed upon the first call to CPA encoding. Subsequent calls to CPA encoding, one CPA encoding, don't do anything, so the adversary can obtain only a single ciphertext encrypted under the key pair. These libraries are written somewhat differently than in the definition of one-time secrecy for SKE, since here the adversary is allowed to CPK before choosing its plaintext. proof. The proof uses the following family of hybrids parameterized by an integer age. Okay, no, I mean, it seems like it would be intuitive as why this would be the definition, right? Um, yeah, you encrypt, you're allowed to encrypt once here and then here, the same thing. It's one-time secrecy. Okay. So I think we're good to go with this. An analogous property is true for CCA security as well. Any PKE scheme that is CCA secure for a single encryption is secure against many. Its proof is mostly the same as the previous one, and it is left as an exercise. So it has the same structure, which is interesting. Um, okay, if C is equal to C star, sure. Okay, this library does not maintain a dictionary as in the usual CCA security definition. This library generates only a single challenge ciphertext, so it would assign only one value to the dictionary. We simply rename this to M star. Okay, yeah. El Gamal encryption. Using the tools that you have learned about so far, how would you propose two users exchange secret messages when they don't have any shared secret key? First, they could run a key exchange protocol to establish a shared key. Then they could use that key to encrypt their secret messages under a symmetric key encryption scheme. They can use Diffie-Hellman for key exchange, but what would be a natural choice for the symmetric key encryption scheme? In the previous section, we saw that it is enough for a PKE to be secure for only one encryption. Thus, perhaps they can consider something as simple as OTP. And since Diffie-Hellman outputs a key that is a cyclic group element, they could use a variant of OTP that uses the cyclic group operation instead of XOR. If Bob wants to send Alice a private message M following these recommendations, it looks like this. Interesting. So now OTP. Oh, what? Let's see. If Bob wants to send Alice a private message M following these recommendations, it looks like this. A is sampled randomly, so this is just the key exchange, right? Okay, so now we think of the message as a group element and we multiply it by the key. Perfect. We send it and then recover the message by multiplying by k inverse. How? Also, shouldn't this be on the left side, right? It should be on the left side just so that they can cancel out. Whoa. Whoa. Okay, what have we arrived at here? How is OTP able to be reused? Okay, that's, whoa, what the hell? Okay, so first thing we do is we convert M to a group element, we multiply it with the key, that is a ciphertext. And then we multiply by the inverse of the key. The thing is, oh well, I guess it's a ticket group, so it's, yeah, sure. So it's a Boolean. Yeah, and so it wouldn't really matter what order it is in. Okay. Sticker groups are abelian, and therefore there's no problem with that. Also, can we guarantee inverses? The answer is yes, because we always make sure that the order of the group is prime. Right? So primeness implies that there are no shared. Okay, yeah, and then there's always inverses. So we're always to recover. Damn. It's pretty interesting. If this picture makes sense to you, then you already understand our first public key encryption scheme called El Gamal encryption, after its creator Taher El Gamal. Yo, the goat. The goat. Dar El Gamal. Wow. Interesting. El Gamal encryption is what you get when you label Alice's message the public key and label Bob's two messages as the encryption of M. Hmm. Wow. Let G be a cyclic group of order n with generator G. El Gamal encryption is defined by the following algorithms. Yeah. Wow. Compared to the picture above, we have renamed values as follows. Yeah. Claim 15, security of El Gamal. If the DDH assumption is true, then El Gamal encryption is CPA secure. The proof is that, well, from claim 14.2, it suffices to prove no way OTP is finally useful. Yeah. So I think that message was already there. I just read it silently, but yeah. Ah, let's stretch. There you go. From claim 13.2, it suffices to prove that El Gamal is secure when encrypting one ciphertext. In other words, we will show that the following two libraries are indistinguishable. Sample, sample, we return the public key always. If C star is undefined, then we sample something random, get this guy, pound the public key. Okay, sure. Well, I'll just stop this. The Fujisaki Okamoto construction. In this section, we describe how to efficiently convert any CPA-secure public keys encryption scheme into a CCA secure one. So chosen ciphertext secure one. The construction slightly breaks the usual abstraction of an encryption scheme in an interesting way. What? Okay, definition 14.4.1. An encryption algorithm ENC is randomized. Oh, sorry. Is randomized, but in this section, it will be useful to run the encryption algorithm with some externally determined random choices. We write encryption pk, m, and then r to denote the result of running enc pkm, but setting the random choices of enc to be r. It is traditional to use a semicolon to separate the last argument. Note that enc da 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 with the randomness as an explicit third argument refers to a deterministic algorithm. Using this new notation, what we will usually write as enc pkm refers to this process. Makes sense? So you have here an example. The El-Gamal encryption algorithm chooses an exponent r as its randomness, so r is equal to z and above. Writing the encryption algorithm with this randomness as an explicit argument gives... it gives this. Okay. In this section, we will assume that every encryption algorithm's randomness comes from, strings of lambda many bits. This is without loss of generality, right? Because an encryption algorithm may use its randomness argument to seed a PRG and obtain as much randomness as needed. Okay, so random generator, okay. The Fujisaki Okamoto construction is a recipe for converting a CPA secure PKE into a CCA secure one in the random Oracle model. Its main idea is to encrypt, on the CPA scheme, plaintexts of the form X using h of x as the randomness. When the receiver decrypts a ciphertext, she would check that it was encrypted with randomness h of x as expected, by re-encrypting it herself with that randomness, and reject it if it's not the case. You may wonder why using h of x for encryption randomness is useful for CCA security. Resendesk RT. Do you understand all these math formulas like enc, pk, x, blah, blah, blah? or is something new as well? So we've been seeing their definitions as we've been going through the readings. So we know that enc refers to the encryption algorithm, PK is the public key, M is the message, R is a random value. So yeah, we've been just going through them. The only one would be H, right? Like H is probably mentioned somewhere, but we don't. We maybe skip that section. Let's see. Can we derive what H is? So, I imagine this is just, right, using this guy as the randomness. So it's probably some sort of random generator. Some pseudo random generator, something like that. Oh yeah, it's an oracle, right? It's a random oracle for this guy. Harmonic numbers, I guess. Okay. You may wonder why using HFX for encryption randomness is useful for CCA security. The reasoning is subtle and clever. Valid ciphertexts must have the form this. And in the random oracle model, it can be argued that you can't produce a ciphertext of this form without first calling the random oracle at h of x. But if the adversary has previously called the random oracle at input x, then the library has a chance to compute the ciphertext c equals enc, right? And remember the association c to x for later. The library is able to know that the decryption of C should be X, but it has deduced this fact without using the private key. When the library no longer needs the private key, we can apply the CPA security of the underlying PKE. You may wonder why using HFX for exertion. And in the random oracle model, okay, if the adversary has previously called the random oracle at input X, then the library has a chance to compute ciphertext C and remember the association C goes to X for later. The library is able to know that the decryption of C should be X, but it has to deduce this fact without using the private key. When the library no longer needs the private key, we can apply the CPA security of the underlying PKE. Oh, so this just refers to the form of a chosen ciphertext attack where you must prove the equivalence between these two libraries, right? Where you're able to remember what the cipher was. I think it's better here. You have like access to a dictionary. Here, right? Okay. I'm understanding correctly, hopefully. For technical reasons, X is not the actual plaintext, but has the form X equals MS, whereas it's chosen uniformly, so basically a salt. Thus, an encryption of M has the form encryption this guy, this guy. Okay? Fujisaki Okamoto. Let sigma be a PK. Do you know what a random oracle is? I mean, I sort of deduce it from the definition of an oracle as it's used in Turing machines. A magical program that can just give you the answer to something. And I imagine a random oracle is just an oracle that produces random output for the same input. Truly random output, right? Yeah, okay. Yeah. So it just produces random output for the same input. Yeah, perfect. For technical reasons, X is not the actual plaintext, construction. So Fujisaki Okamoto. Let sigma be a public key encryption scheme, and H be a random oracle with lambda output bits. Assume that sigma enc uses lambda bits of randomness. Then the Fujisaki Okamoto PKE scheme consists of the following. So you have sigma star, and okay. Okay. And sigma star encryption becomes. So we so for some reason adding Not that many bits of randomness here, which is what it was promised. Then this encryption works as grab a random salt of sorts, grab R, and then grab the random oracle, attach M to it. Sorry, M attached to it the salt. Then we have C equaling the encryption. Okay, then we return C. Sure. Sure. Okay, so sure, I mean, we just encrypt the message with the salt appended to it. Then decryption works by saying decrypt whatever was given to me. I get M and then the salt. R is just, oh, we get the same choices. Oh, if C is different from sigma encoding, return error, otherwise return M. That's interesting. If C is different from sigma encoding PK command, sure. See the chat. Resin Descartes. Yes, this is indeed the link we're using. It's a model because random oracles are not real. Yeah, just like, the usual oracles. Yeah. Random oracle chooses random number it never saw message before, but if it saw, yeah, exactly, yeah. I mean, yeah. We'll prove the security of Fujisaki Okamoto using the following assumption about the underlying CPUs. Yeah, it's just like an oracle machine, well, an oracle when it comes to Turing machines, and then you just add the property of randomness where you say, okay, have I seen this a bit before, and then return it. Okay, yeah. We will prove the security of Fujisaki Okamoto using the following assumption about the underlying CPA secure scheme. Definition 14.4.4. Unique randomness for PKE. An encryption algorithm ENC has unique randomness if for all PK and LM, the function encoding is one-to-one, is injective. Has unique randomness if for all PK and all M, the function this is injective. So independent of... Okay. At each instance of PK and M, this function is injective. So independent of the random choices you make, there's gonna be one and only... Yeah, it's just gonna be injective with respect to the random choices you make. This property makes the Fujisaki Okamoto construction easier to prove, but security can also be proven without it. Suppose sigma is a CPA secure PKE scheme with unique randomness. Then this construction is CCA secure in the random oracle model. From claim 14.2, it satisfies to show that the scheme is CCA secure with respect to a single encryption. In other words, which we saw why, right? I think I'm running out of battery. Kind of. In other words, if you have these libraries be equivalent, yes, then you get... Okay, so... Whoa, what's going on here? We have one CCA, yes, one single encryption, where we say, okay, sure. Then once the decryption would work by M appended to the salt, is defined as this. And then otherwise we just reproduce the entire algorithm. Okay, perfect. Proof. One important idea in the proof is that an adversary cannot create a valid ciphertext if they have not already made the expected call to the random oracle. We formalize the idea as follows. Ah, if enc has unique randomness, then the following algorithm returns true with probability almost 1 over 2 to the lambda. So we guess K and then X go with C. We pick R to be random, yes. The subroutine generates an encryption of X and returns true if the caller successfully predicted the resulting ciphertext. The encryption randomness R is playing the role of a random oracle output that has not yet been sampled or observed. There are 2 to lambda choices of R, and since enc has unique randomness, each choice of R leads to a distinct outcome C star. Since the caller's guess C is fixed before C star is chosen, yes, uniformly among 2 to the lambda possibilities, the algorithm returns true with probability n minus 1 over 2 lambda. It may also be the case that C is not one of the 2 to lambda possible ciphertexts, in which case the probability is 0. The formal details of the proof follow. Okay, I mean, I imagine, right? This is the bad event has negligible probability if the adversary makes Q queries to the random oracle, then at the end of time, A contains at most Q values, and the bad event happens with probability at most Q over to the lambda, which is negligible. Okay. Real world impact. Because the Fujisaki-Okamoto construction adds CCA security to a PKE with almost no overhead, it is used in many candidate standard, public key encryption algorithms. The US National Institute of Standards and Technology recently held a competition to standardize the next generation of public key encryption schemes, holding the first round of submissions in 2017. Out of the 46 PKE schemes proposed, 25 used the Fujisaki Okamoto technique to achieve CCA security. All 4 schemes that advanced to the final round of the selection process used Fujisaki Okamoto or similar variant. Pretty good. Hybrid encryption. Public key cryptography is much, much slower than symmetric key cryptography. As a simple demonstration, one invocation of the AES block cipher requires only a few CPU cycles, but encrypting in a PKE scheme can take millions. In this section, we explore a clever way to get the best of both worlds, the features of PKE with costs as close as possible to SKE. Suppose Alice has published her public key PK and Bob wants to send her a large file. Using PKE directly on a large file would be incredibly expensive. Instead, Bob can do the following. Sample a fresh key K for a symmetric key encryption scheme. Encrypt K on the PK using PKE and send it to Alice. Although PKE encryption is slow, we are encrypting only a small value, which would be the key. Encrypt a large file on the key that's intended for symmetric, and send it to Alice. SKE encryption is fast for this large file. When Alice receives this data, she can decrypt the PKE ciphertext to learn K. Then decrypt the SKE ciphertext with K to obtain the large file. The overall functionality is the same as PKE. Bob can encrypt the data to Alice, knowing only her public key. Makes sense, right? We encrypt the keys instead of the actual data, then we use those keys for symmetric, and then we're good to go. This method of public key encryption is called hybrid encryption, where hybrid in this context means that the scheme consists of a combination of PKE and SKE. Okay, no, the concept makes sense, right? The construction is just a formalization of what we just read. Each ephemeral key is used to encrypt just a single plaintext, and therefore the symmetric key scheme only needs to have a one-time secrecy for the overall hybrid scheme to have CPA security. Okay. If sigma PKE is a CPA secure PKE and sigma SKE is a one-time secret SKE, then hybrid encryption is CPA secure? Proof. The proof is an easy consequence of the definitions. Yeah, okay, that makes sense. The situation of CCA security for hybrid encryption is more subtle. Our usual way of using the real or random paradigm to define security doesn't quite work, in the sense that even if both the underlying PKE and SKE are real or random, CCA secure, the resulting hybrid scheme may not be. Oh. There exists a real random CCA secure PKE, sigma PKE, and a real or random CCA secure SKE, sigma SKE, such that the resulting hybrid encryption is not real or random CCA secure. Okay. However, if we consider the left or right paradigm for CCA security, then the property we hope to be true about hybrid encryption is true. Hybrid encryption achieves left or right CCA security if both its underlying PKE and SKE do. Okay, I remember we skipped the left or right section. We do know the other definition, so I think we would be fine with that one. Proofs of these two claims are left as exercises. Hybrid encryption is the only example I know of a completely natural encryption scheme for which the distinction between left or right and real or random security is significant. In every other case, the encryption schemes we care about in practice satisfy both flavors of security. Key encapsulation. But we have a long way to go. Okay, let's see. Because of hybrid encryption, there is rarely any need to use true PKE for anything other than encrypting uniformly sampled values. A key encapsulation mechanism, KEM, is a specialized public key encryption that is capable of only that. It can encrypt only pseudo-random plaintexts. Oh. In a PKE, we tell the encryption algorithm our choice of plaintext, but in a KEM, we let the encryption algorithm itself choose the plaintext. Although this might seem like a strange modification to make to a PKE, the benefit is that a KEM ciphertext can be shorter than a traditional PKE ciphertext. Yeah. I mentioned, I skipped the explanation of left or right. Yeah. I said, yes, we skipped it, but we know the other definition, so we're fine on knowing what the claim was saying. Basically, instead of comparing two libraries, one of which is random, you compare calls of functions if you can distinguish it from it's not secure. Okay, I see. That's interesting. Yo, let's go. But yeah. Okay, definition 14. A key encapsulation mechanism consists of the following algorithms. Keygen, which is the same as the PKE scheme. Encaps, a randomized algorithm that takes only a public key as input and returns both the ciphertext and plaintext. And then decaps, same as in the PKE scheme, a deterministic algorithm that takes a private key in the ciphertext C and returns plaintext M. A KEM is correct if the following process output is true with probability 1. Okay. So this is almost like sharing some sort of secret. Right? Because it's like a secret generator. You give me the plaintext, I give you this thing. Okay. The definitions of CPEA and CCE security for KEMs are similar to those of traditional PKE. The adversary CPE enc interface now takes no arguments, since a KEM's encaps algorithm does not take a plaintext argument. In addition to requiring that the ciphertext is pseudo-random, the definitions also require that the plaintext is pseudo-random. And of course, independent of the ciphertext, sure. Definition 14.6.2, a KEM sigma has security against chosen plaintext attacks if the following two libraries are indistinguishable. Okay. Generate the keys, return. Okay, we sample randomly, then we return. Okay. Sure. Sure, sure, sure. Oh yeah, you mentioned why we don't need the yeah, sure, the plain text. Anyways, definition 14. A chem sigma has security against chosen ciphertext attacks if the following two libraries are undistinguishable. So we basically apply the exact same definition we've been using before. Hybrid encryption is sometimes called the ChemDEM paradigm, where DEM, the symmetric key encryption scheme, stands for data encapsulation mechanism. Just like PKE, if a chem is secure for a single encryption, then it is secure against many encryptions. Hence, we have the following results, analogous to the ones in section 14.2. Because chem encapsulation takes no plaintext argument, these libraries are slightly simpler than their PKE counterparts. The ciphertext and plaintext can be generated at the beginning of time. Claim 15.6.4, one-time security for key encapsulation. Let sigma be a chem scheme. If the following two libraries are indistinguishable, then sigma has CPA security. Okay, this is usual for CPA security. Oh, why is it doing it only one? Oh, yeah, because it's one time. Okay. If the following two libraries are indistinguishable, the same definition we've been using before. Yeah. Okay. The proofs follow the same structure. Yeah, these we're familiar with these. El Gamal Chem. Okay, we're not familiar with this one. One reason for studying chems is that the ciphertext can be smaller than those of a PKE. El Gamal encryption provides a great example. Recall that El Gamal ciphertexts consist of a pair of group elements that have the form G to the R, PK to the R times M. The security proof uh, argues that PKR hides the plaintext because PKR is pseudo-random given PK and G to the R. But if PKR is pseudo-random, why not just consider PKR to be the plaintext and let G to the R be alone be the ciphertext? The result is Gamal Chem, and its ciphertext consists of just a single group element. Oh, interesting. Okay, so everything with El Gamal, it's like use something that's already existing and then add um, a few properties or a different perspective, and then you get a different thing. It's defined by the following. So key generation is as usual. The public key is just G to the power of the secret key, yes. Encapsulation happens by I give the public key, sample a random number, consider C to be G to the R, which is the generator. Then consider M, the plaintext, to be PK to the power of R, which is essentially. This is essentially. Why are they doing the same? So PK is just G to the SK, yes. And PK to the R is just. Okay, sure. And then decaps runs C to the SK. C being G to the R, and then C to the SKs would be G to the R SK, which would be the public key to the R. Okay, sure. Claim 14. So El Gamal Chem is CPA secure if the DDH assumption holds. The proof is extremely similar to 14.3, and it's left as an exercise. Oof, okay. Okay. 2 more hours there. Well, actually, no, that was like more like 1 hour. Okay. Oof, it gets a little bit tiring because of the fact that the reading is dense and it's very long. A single chapter. I need to find ways to make it so that I don't get like a dense mind after reading for so long. Because if I just read, right, the more I read, the more difficult it is to stop and actually pay attention to details because you're like, oh, I'm tired, right? So we can do half stream reading, half stream learning Rust. That's what I was thinking, right? Because I don't know Rust, right? So we still need it for for the blockchain thing. So I think it would make sense to do what Andrew's suggesting. Um, Resin Desk is asking, do you know Rust already, or you have to look things up like blockchain? You know, I have to look everything up. I don't know Rust. Off Market 7, my quant. Brother, what do you mean? Oh, welcome to the chat, by the way. First time. All right, I think we can do that. Right? I think we can do that. It would make it a little more um, dynamic. So then we can use learning Rust as a break. Although, you know, as some chassis have pointed out, we don't know if that's actually going to be a break or it's going to be frustration. But either way it works. Oof. So yeah, I think Andrew's idea is great. I think um, I think we can split the stream in two. Maybe we can do one chapter of cryptography, really read it extremely well, right? Because then if we're only gonna read it, one at a time, then we're able to be like, okay, bam, bam, bam. What is this? What is this? What is this? Then we learn Rust to sort of appease our mind and do something that's more dynamic and entertaining in a sense, or like mind distracting, if you will. And then we maybe continue with another chapter and then learn Rust again. I feel like that would be a good start. Yeah, what Andrew's saying. All right, let's do that. Let's do that. So I think it is good if we take like let's take let's take a 10-minute break. Yeah, 10-minute break. Given that we finished this one chapter, um, yeah, a 10-minute break, and then we'll be back in 10 minutes. Okay. So let me create a timer here. Dude, that timer is like one of the best things I could have I could have taken a look at. All right, people, we're gonna be back in 10 minutes. The starting soon screen is gonna tell you when we're gonna be back. You'll also hear my voice when we come back. But yeah, see you guys. We'll see you in 10 minutes. All right. Hello, everyone. Welcome back. 10 minutes of break, which is great. Yeah. So, welcome back. And today, and right now, we're going to transition to learning Rust because I don't know Rust. So, you're going to see you have a very unique opportunity, right? You're going to see sort of like the the birth of hate or of love. Like right here. Like we're either going to love this thing or we're going to hate this thing. It seems like the community is very divided. Um I want to know what all the fuss is about. So we'll take a look at Rust and yeah. So let's see. Let's see. So the first question would be okay, how do I install Rust? How to install Rust. Like, this is like a total beginner. Install Rust. Oh, what is this website? Okay. Interesting choice of colors. Um, okay. Get started. Okay. Getting started. Quickly set up a Rust development environment and write a small app. So let's see. Installing Rust. You can try Rust online in the Rust playground without installing anything on your computer. No, we're not going to do that. Real men, real programmers. Okay. Roast Up, the Rust installer and version management tool. The primary way that folks install Rust is through a tool called Rust Up, which is the Rust installer and version management tool. It looks like you're running Mac OS, Linux, or another Unix-like OS. To download Rust Up and install Rust, run the following in your terminal, then follow the on-screen instructions. Okay, let's copy this. We're just trusting them blindly. That's okay. Send to the terminal. So we're running proto on this thing. Blah, 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 blah. That's totally fine. Let's see. Ooh, very exciting. Very exciting. Let's see. So we have welcome to Rust. You have an existing Rust up settings file at here. What? Rust up will install the default toolchain as specified in settings file. Default host triple. Why do I have a Rust up thing? Did I ever install something that installed Rust on my PC? I do remember using a tool that was originally coded in Rust, but like I never installed the Rust thing itself. It should have been just a binary. Users, let's see, where am I? Users read slash dot rustup. So it's command dot, right? How do I show the hidden files? Hello, brother. How do I show the hidden files? View. Show view options, maybe here. Show item info. I hate macOS. Okay, how to show hidden files on Finder macOS. It's like command dot or something like that. Command shift period. Okay. That's it. Command shift dot. Yeah, there you go. Dot. Brother, there's nothing here. Oh, never mind. Dot rostup. Delete this guy. I don't want him here. Okay. Half of another application I have gets completely demolished. All right, let's do it. Brother, there is nothing. Oh, it generated it automatically. Okay, well. Welcome to Rust. This will download and install the official compiler for the Rust programming language in its package manager, Cargo. No! Rust has a package manager. No. Okay. Rust up metadata and toolchains will be installed into the Rust up home directory, located at here. This can be modified with the Rust up home environment variable. The Cargo home directory is located at here. This can be modified with the cargo home environment variable. The cargo, rustc, rustup, and other commands will be added to cargo's bin directory, located at here. Oh, sorry, that was the previous one. Da-da-da-da-da, located at here. Pam, pam, pam. You can cargo call detect. You can uninstall at any time with rustup self uninstall, and these changes will be reverted. Current installation options. The default host triple is Arch64 Apple Darwin. Default toolchain, stable one. Profile default, modify path variable, yes. 1. Proceed with standard installation. Customize installation, cancel installation. I imagine we proceed with the standard. Ooh. Clippy! Clippy! What are you doing here? Clippy! Welcome home. Welcome home, Clippy. But yeah. What is this Clippy guy? Cargo is the package manager, they just said it. The docs are for some reason super huge. The Rust standard, I imagine, is some standard library. Rust C may be the thing, the last translation between C and Rust. Rust formatter may be the FMT. What is Clippy? What is Clippy? Let me update the title of the screen. Learning Rust. Let me see. Learning Rust. All right. New title of the stream. Learning Rust for the first time. All right. All right. So we see this stable da-da-da. Rust is installed now. Let's go, people. Let's go. To get started, you may need to restart your current shell. This would reload your path environment variable to include cargo's bin directory. To configure your current shell, you need to source the corresponding end file. Yeah, sure. Usually done by this. Yeah, this is the usual thing. Perfect. So, what else does the guide say? It says, is Rust up to date? OG Clippy. This Clippy is a linter for Rust. Oh, okay, I see. Yeah, because I was like, Clippy, Clippy, welcome back. Of course, I thought it, right. I didn't think it was the OG Clippy, because why would it be here? But, yeah. Is Rust up to date? Rust updates very frequently. If you have installed Rust up some time ago, chances are your Rust version is out of date. Get the latest version of Rust by running Rust up update. Cargo, the Rust build tool and package manager. When you install Rustup, you'll also get the latest stable version of the Rust build tool and package manager, also known as Cargo. Cargo does lots of things. Build your project with Cargo build, run your project with Cargo run, test your project with Cargo test, build documentation for your project with Cargo doc, publish a library to crates.io with Cargo publish. To test that you have Rust in Cargo installed, you can run this in your terminal of choice. So let me transfer the browser to the first workspace. And so let's try all of these. Let's try Cargo. Well, I guess we have to reset this. I honestly don't really care. Let's see, Cargo dash version. Sorry, I need to close this thing and open it again. Could have sourced, I know, but I just don't want to do that. Perfect. Cargo dash version. Ooh. Okay. Turns out OG Clippy was bad because Microsoft threw away their own research on how to make it not bad and made it bad intentionally. Really? Damn. Poor Clippy. The cargo book? Bro, what the hell is the cargo book? Brother, if we need an entire book to understand what this little guy does, I'm already scared. Oh no. Okay, yeah. I hope not. All the tools. Rust support is available in many editors. So imagine in VS Code, I install Rust Analyzer, right? By Matt Clad. Generates a new project. Okay, okay. Ooh, let's write a small application with our new Rust development environment. To start, we'll use cargo to make a new project for us. In your terminal of choice, run cargo new hello Rust. Yeah, Matclad is the good. It's like actually one of my idols. Like not kidding. MKDA tutorials, I think. Well, I think I already have a folder like that. Yeah, CD tests. So let's do it in tests. And let's run cargo new hello Rust. Perfect. So I imagine we open this with code. Code hello Rust. Yo, the power of the sun in the palm of my hand. Okay, there you go. Manage, trust. Perfect. All right. Oh, oh, that's fine. Okay, this will generate a new directory called hello Rust with the following files: a cargo toml, slc, and the main.rs. So, cargo toml is the manifest file for Rust. I imagine like the packages for Node, right? Okay, perfect. It's where you keep metadata for your project as well as dependencies. Yeah, SSC main RS is where we'll write our application code. The cargo news then generated a hello world project for us. We can run this program by moving into the new directory that we made and running this in our terminal. Funny how the cam is always like when you open the editor. Yeah. Unfortunate. VS Code disadvantages, but it's okay. Oh my god, our first visuals of Rust code. Brother, let's go. Okay. We can run this program by moving into the new directory that we made and running this in our terminal. So let's see. Let's see. Let's open the terminal. If it ever opens. Yeah, there you go. So we go hello Rust. Okay, despite it being in the SLC folder, there's no need for me to do anything, right? Cargo run. Compiling. Damn, that was slow for a hello world program. Okay, let's see. Cargo run again. Hello world. Yay. You're a Visual Senior Rust developer, just a zero is insane. Anyways. But yeah, we got our first program running. Yo, let's go. People, this is the future. Rust is the future, bro. What are you talking about? Profile default? Hell no. We're gonna create a new profile just for Rust. New profile. Let's go. Oh shoot, this thing is okay. Rust. Rust. Somebody give me a beer. You're gonna compatibles are as bad. Brother! Do not trash on C++. Mm-mm. I'm not sure if I want to inherit some of the extensions. Well, yeah, let's inherit from the C++ one, and then we create it. And then we just delete whatever we don't want. Okay, perfect. So let's go to the extensions, restart the extensions, and then I'm just gonna disable. I'm sorry if language is so bad, someone needs to trash on it. Brother, do not say that. See, now you guys are making me be on the side of Rust. Like, if you're doing this to C++ without any sort of motivation, brother, like, I cannot trust your word when it comes to that. Oh shoot! No, 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 no! I didn't want to do that in the default profile. I want it in the Rust profile. Oh, what? Buddy, I asked for my extensions to be installed. What what happened? No. The world is now gray. Bro, what is this, brother? What is this? What is this? Oh no. Okay. So what do we need to do? Like, is my theme still there? Color theme. Do I just need to select? Oh yeah, okay, okay. Okay, okay. That was a little scary. File icon theme, we want material icon theme. Perfect. Perfect. Okay. And so now we're gonna look at the installed extensions and we're gonna, you know, eliminate anything that we don't need for Rust. So we don't need this. Errorlins we want Excalibur, yes, yes. Remote SSH, I mean, sure, right? These guys are pretty fine. Trading spaces, yes, I want that. Yes, I want this. Yes, Clang D. Well, I actually don't want Clang D because I'm not gonna use it. Not gonna use that, not gonna use that. Code LLDB, I don't need it because I'm not in C++ anymore. Common divider, yes, we need it. Debug tracker, hell no. Oh wait, actually, oh, yeah, okay. We don't need the memory view guy, and we also don't need the debug tracker. Um, wait, guys. Sorry, wait, is it still lagging? Is it still lagging? Wait, let me know, let me know. Let me know if it's still lagging. Um, Resindesk says, I'm just like, you're reading that cryptography. I was trying to figure out an hard lead code problem called trapping rainwater. These things are dense as I make us smarter. Yeah, the trapping rainwater lead code problem is like, it lives in my mind. It lives in my mind, yeah. There's a little bit of lagging, or is it me? Abby, trying is welcome. YH is lagging. LDB is still useful for Rust debugging. Oh, well, never mind. Never mind. Let's go back. Let's put LLDB back into the LLDB. LLDB. Oh no. It's okay. We'll install it eventually when we actually need it. Currently not lagging, but when you click in your editor, it lags. Yeah, that's a given. That's a given. VS Code just like boom consumes everything and turns everything down. Um, we don't need the makefile tools. We don't need the memory view. We don't need version 482. This was for a course of mine for start extensions. Perfect. Seems like it worked, right? Seems like we're back on track. Back on track. All right. How do I make it so that these things don't appear here anymore because they are not installed? Ah, get out of here. Get out of here. Reset. Reset. Window. Reload. Bye bye lag. Oh no, lag. Hello, are we back? We're back. Yes, we're back. Okay. Sorry about that. Notice that if I do, if I no, it's because I clicked reload window, and so it like it makes VS Code start again, and so I just start lagging a lot. But hopefully you guys are here now. Um, yeah, refresh the stream because it's very likely you're like 10 seconds behind. Just like refresh the website and then come back. But yeah, so we pruned the extensions and now we have only 16. Let's actually reduce that even more because I think we are able to uninstall dev containers. We don't need that. We don't need the hex. Well, nah, we need to uninstall that too. We don't need remote SSH. We don't need the tunnels. We don't need remote development. We don't need the remote explorer. The PDF one we do. Um, Restart extensions. What MacBook do you use, by the way? I use one that has an M2 chip. Even uninstalling causes lag. Really? Oh no. All right, people. One last one, right? Because these are the only extensions we didn't use. One last one. It's going to lag, okay? Because I'm going to reload the window so that the changes can take place. I'll see you on the other side. Are we back? Is this the other side? Is this the other side? Are we back, people? I think so. I think we're back. I think we're back. We're in the glory of going back. Yes, okay, yo, let's go. We all survived. Okay, now we only have 8 extensions out of 26 that we originally had. Those other 26 are used like frequently, but not with Rust, right? Because most of them were the C++ development ones and the remote development, which I use for college. Perfect. All right, people. We are so back. We are good to go. Okay. So. Into the maybe 3 minutes, maybe 2 minutes. um, Perfect. Adding dependencies. I do not want to know this. So one question. There's something I have. There's like a kind of fear I have with dependencies, and it is whatever JavaScript has. Like the whole Node.js, right? npm package manager makes Node and JavaScript be like one of the worst places like ever, right? So it's like, you know, does the fact that we have a package manager imply that Rust also have those disadvantages? Also has those disadvantages. Um yeah, okay. But is Rust the exact same? Right? Because NPM has like this very big issue where like people just install packages for everything. At least when I read some of the JavaScript code, it's like package. And it's like, if you go and take a look at a node modules folder, you have like 120 folders in there. What are we doing? Like, is it the same thing with Rust? Yeah, Rust is the same, brother. No. Okay. It's okay. It's okay. Um, Rust standard library is really, really small, so you will need dependencies for random numbers even. Ryuk 2285. No AI? Seriously? Yeah, no AI. Rust is not known for NPM. Yeah. There is an NPM package just for checking even numbers. Yeah, there's an NPM package for anything. It's not as bad, but still pretty bad. So what is this YouTube video? It's gonna lag again, probably. Oh my god. Oh, is this a conference? If it is, I don't think we have the time to watch it, but which ones use package managers created? What? Bro, what? Brother, this is absolutely insane. And then there's Rust. Okay. Rust is still at a pretty good spot, I would say. Still kind of annoying, but I mean, it's interesting that it's more than Python, which is absolutely insane. I cannot believe it's more than Python. All right. Perfect. Let's see. Resin Desk, do you listen to any music or is it bad for concentration, like studying or working? Uh, okay, so I listen to music if I'm doing a repetitive task, because then it makes it entertaining. Otherwise, I don't listen to music because it doesn't let me focus. Like if I'm writing code that I want to focus on, listening to music is really bad for me. If I'm writing code that's repetitive, I'm like, yo, let's have some music and listen to something. Meliodev, don't you have uBlock Origin installed in your Firefox? No, I don't. It's number of dependencies used to create a website about the language. Oh, I see. If the programming language provides a package manager, people tend to automate dependency hell. Yeah, yeah, yeah. Like, it is a problem because then you don't know what you're importing and you just bring it into the project being like, oh, yeah, let's go. Right? Uh, it's just like the left pad situation that happened like, what, 3 years ago, probably? Where some random left pad package, like a function you could just write yourself in like 2 minutes. And people are just importing that as a package. Not only do you introduce like the overhead of actually importing and so on. Um, so yeah, think you should install at least uBlock in your Firefox so you don't have any YouTube ads. That is true, although like ads I think are important in the sense that for the people that I watch, right, I want them to actually receive the compensation that you know, that they have and etc. And not only that, there are some ads that are like actually entertaining. So I don't know. Mainly from the perspective of a creator, I would want them to like if I'm benefiting from whatever I'm watching, like even if it's a little, at least abide by the policy of that. Itachi is back. I'm back. Sorry, lol. Rare ad enjoyer. Yeah, no, no. I wouldn't say an ad enjoyer, especially when the ads are like from AI companies and stuff like that, or like AI ads. I'm like, dude, come on. But yeah, because I do it for the person on the other side of the content. But yeah, all right, let's take a look at this. So I don't want to add dependencies, at least not for now. I just want to write. So okay, I am familiar. Well, not familiar, right? Are you just starting? Yes, Nico address. Like we just installed Rust. I'm familiar with the concepts of Rust. Like familiar, not familiar. I know about the borrow checker. And the reason for that is because I took a programming language design class, and Rust was in there in the borrow checker model. We didn't dedicate basically any time to Rust, but it was mentioned. So I do know, I have heard of the borrow checker, right? And I kind of understand what it's trying to do, but we're going to have to learn this from the beginning. Okay. Now let's write a small application with a new dependency. Add the following code. Ferris says say. Say this much. Hello from Rust Stations. Oh, and it generates this little guy. Wait, that's so cute. Little Ferris. Ferris is the crab's name, right? Yo, learn more. Who's this crab? Ferris. Ferris is the unofficial mascot of the Rust community. Many Rust programmers call themselves Rustaceans, a play on the word crustacean. We refer to Ferris with any pronouns, she, he, they, it, etc. Ferris is just Ferris. Ferris is a name playing off of the adjective ferrous, meaning of, oh, or pertaining to iron. Wait, that's pretty clever. Since rust often forms an iron, it seemed like a fun origin for a mascot's name. You can find more images of Ferris on crustation.net. Rustation.net. Yo, ho, ho, Ferris. Yo, let's go, Ferris. I am Ferris the Crab, unofficial mascot for Rust. Yo, yo, Ferris. Ferris is pretty cool. I like Ferris. The fact that they have a mascot actually improves the language so much. I love this guy. I love this guy. Anyways, um, so how do we learn Rust? So, great question, right? Like, learn, I suppose. Learn Rust. Read the book. Oh no. Oh no. The Rust by example or the Rustling course? Oh, wait. Is this exercises? Yo, let's go. I feel I prefer this one, right? Small exercises to get you used to reading and writing Rust code. Yo, exercises, that's the best. Small exercises to get you used to reading and writing Rust code. Visit the website for a demo, info about setup and more. Ooh. And what is this? Rust by example? Oh no. Oh no, it's text. It's text. I don't want to read. I don't wanna- Oh no. Mm, it's okay, I suppose. I suppose. Okay. Okay, let's see this. Rustlings. Let's see what rustlings is. Oh, is this the terminal thing that I think it was Andrew who shared his terminal through one of these. Okay, anyways. Yep. Yeah. Ask anyway. Yeah. Those will be fun. Rustlings and then init. Okay. Oh yeah, recorded with Askinima. CD rustlings. Rustlings. Okay. Okay. Quick start. Create these. Sure. So which one do we do, people? Which one do you think is the best? Rust by example or rustlings? The book, brother, that is not an option. Okay. Um I think maybe rustlings because it has actual exercises. Yeah. Rustlings Ganga Kamau. Okay. In recording, they also use Helix, Rust Terminal Editor, and Zelish. Mmm, pretty good. All right, so I guess we can like have them side by side, maybe. Let's take a look at the setup. So setup here, small exercise to gauge your parameter, quick start. Oh my god, it's a package. Oh no. Oh no. Okay. So I imagine it is in my best interest to do this in a different folder, probably. Terminal, and then I do cd projects, cd tests, and then, well, I guess not tests, right? I would like to create a mkdir tutorials, mk cd into tutorials, and then we run cargo install rustlings. So are the global packages? Are the packages local? What's the thing here? I think it lets me just do it here, so I assume all the packages are just global. Cargo installed installs the binaries, so it's not really a package. Oh, I see. mkcd creates and enters into the directory. On macOS too? Because I know it's like it's a usual shortcut that people implement in their own implementations of. That's a lot of code to compile. Yeah, this is our blockchain, brother. We finished it. But it is a package, but it is called different. They're called crates. Okay. They're just the same evil with a different name, which doesn't really change the fact that it's an evil. 88 dependencies. Yeah. Well, yeah. It's normal. Yeah. Yeah, we figured. The most complex Rust app I've written has less than 30 dependencies. This is wild. Brother, what do you mean it's wild? No. Every Rust project needs to have on the ballpark of 80 to 100 dependencies to be considered a real project. It's just that you don't write real Rust projects, buddy. You don't know. You don't know the way. Don't blame your inexperience on other people's projects. You know, we're gonna do it the right way. The clap builder. Oh my god. What are these things? True. You just don't know the Rust way, buddy. Ah. You aren't a real Rust dev if you don't install 200 devs. Hello world. The wait 2 minutes. Yeah. All right, people. We did it. We did it. Let me make sure that we didn't. Yeah, there's nothing here. That's great. So it says rustlings in it. Do you see the rustlings from in it? Okay. Let's go CD rustlings. Perfect. So we get that. And then starting rustlings. Is this your first time? Don't worry. Rustlings is made for beginners. We're going to teach you a lot of things about Rust. But before we can get started, here are some notes about how Rustlings operates. Let me put this full screen so that you guys can see. And there you go. The central concept behind Rustlings is that you solve exercises. These exercises usually contain some compiler or logic errors which cause the exercise to fail compilation or testing. It's your job to find all errors and fix them. Make sure to have your editor open in the Rustlings directory. Rustlings will show you the path of the current exercise under the progress bar. Open the exercise file in your editor, fix errors, and save the file. Rustlings will automatically detect the file change and rerun the exercise. If all errors are fixed, Rustlings will ask you to move on to the next exercise. If you're stuck on an exercise, enter H to show a hint. If an exercise doesn't make sense to you, feel free to open an issue on GitHub. We look at every issue, and sometimes other learners do too, so you can help each other out. Wait, this is actually a pretty interesting tool, right? Seems like excellent. Output. So welcome to that Rustlings. This exercise compiles successfully. The remaining exercises contain a compiler or logic error. The central concept behind Rustlings is to fix these errors and solve the exercises. Good luck. The file of this exercise is exercises/00 intro. Okay, have a look. The current exercise path will always be shown under the progress bar. You can click on the path to open the exercise file in your editor. Yay. Yay. Oh. Yay. Hello? I cannot click on the path. Ah! Okay. Let me bring this to workspace. So this guy goes to 3. This guy doesn't get to go full. We open Visual Studio Code again. Oh no, the lag! Oh no! Are we back? Okay, yeah, I don't think I lost you. Great. So, let's open a folder. Then we go to projects, tutorials, rustlings, exercises. Well, I imagine I just open rustlings and then I can just go into the whatever thing. Perfect. Manage, and then I trust you with all my heart. Okay, I imagine I don't need this view. I think I can just go open folder and then just open the exercises folder, maybe. I think that's better. Yeah, okay. Okay, perfect. Oh my god, the amount of exercises. Okay. So what are we doing? What are we doing? What are we doing? We say 00 intro and then intro 1. Yo! Our first rush program. Is this our first rush program? Okay. Oof. Okay. We sometimes encourage you to keep trying things in a given exercise, even after you already figured it out. If you got everything working and feel ready for the next exercise, press enter. Enter N in the terminal. The exercise file will be reloaded when you change one of the lines below. Try adding a new println and check the updated output in the terminal. Let's go. So println star, and then I can say, hi mom, I made it, semicolon. Oh, what happens if I don't include the semicolon? Um, hello? Checking the exercise intro one, please wait. Wait, I don't know if you guys can see what I see. I see this. Checking that exercise, please wait. Brother, semicolon. Did we just break rustlings? Checking the exercise intro one, please wait. Brother, are you okay? You will wait because VS Code has a lock. To the right, because Rust Analyzer is working. Oh, I see. Well, this is a great time to go get our daily dosage of Frosted Flakes. Let's see. Ah, perfect. It's perfect for the occasion. I'm gonna celebrate learning Rust. let's let's see. Why do you talk to me? I never needed to do. All right, I'm gonna grab a spoon from the kitchen. We got the spoon from the kitchen. I am coming back now with the spoon from the kitchen. Okay. Oh, it seems like it finished. No, it didn't. Duration, thread sleep, yeah. Blazingly fast. The face of that guy is like such a funny expression that it's like perfect for situations like these. Yeah, that's funny. All right, let's wait. Oh, Rust Analyzer finished. Oh, yay. Okay. Maybe MadCloud was not cooking after all. Yeah. So, what if we delete this line? Checking the exercise intro one, please wait. Oh my god, no! Rust Analyzer is running again! No! Bro. Dude, if it's gonna be this way all the way, I'm like genuinely going to crash out. I'll be trying this. It says, yeah, no, I know it says exercise done. I've just been trying to check out the like what happens if I have a compilation error. What will the terminal say? Right, bro? You're on power saving mode. What do you mean, brother? Like, okay, let's let's remove it, right? Let's try and see what happens. Okay. And what happens if I now delete the semicolon, which should produce an error, I imagine? Well, wait, is that the reason why? Have I just had the low battery mode and all of this time that's the reason why everything has been lagging? I refuse to believe that. Oh no. Wait. Wait, is that the reason why? Am I just stupid? Wait. Okay, one test. We're going to reload the VS Code window, right? Now it's not. No. It's been like that all this time. All this time. I disabled it just now. So let me reload the window and we're going to test if this thing lags while I reload the window. You're a doof. Yeah, dude. Okay. Dude, no, wait. How did I not notice? that it was in power saving mode for 3 weeks, bro. Okay, okay. Let's try and reload the window. Is this the thing? Is this it? All right. If it lags, we'll see. Three, two, one. No, 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 no. And it loaded in like 1 second. Bro. Dude. Oh no. Bro. So many issues. So many issues we had been having. And people were like, dude, what is your PC? And I'm like, yeah, mine is an M2. It should be fine. And everyone would be like, dude, that's crazy. And I'm like, yeah, that's crazy. No way. Everybody, we need to pay respect to Sir Elfman for noticing what I didn't notice in 3 weeks, but also none of you noticed in 3 weeks. Brother, Sir Elfman is our savior. Our Lord and Savior, Sir Elfman, you're baptized from now on as our savior. Thank you, Sir Elfman. Um, Power saving mode, although it's plugged. Yeah, yeah. Joe, you're really nice Mac now. So I think it was normal before. At some point in time, probably at an airport or something, when coming here to SF, maybe I activated low power and forgot to turn it off. Give him VIP. On battery, I love using. Yeah, yeah. So that's probably why. Maybe I had low power save mode and then I just forgot to turn it off. I don't know how to give him VIP. How do I give Sir Elfman VIP? Slash VIP or something like that? What does VIP do? What does VIP do? What does VIP do on Twitch? A special recognition role that grants a distinct chat badge and like chat immunities. Another servant as a token of appreciation. Special badge that displays a shiny pink purple diamond icon next to the user's name in the chat. Allows users to chat during slow mode, subscriber only, or follower only restrictions. Permits posting hyperlinks in chat even when links are otherwise disabled or filtered, and bypasses standard chat rate limits. Yo! Can I do that without being affiliate? Maybe. See ya, y'all. Oh no, Sir Elfman. Okay, when you come back, we're gonna give you VIP. And we should also give VIP to Andrew, because Andrew has been the GOAT. And Net Borsa. Probably strychnine. So, yeah. Is Big Diamond near nickname? Okay. Well, let's see. VIP. Can I put Andrew Kraevsky? Yo! VIP Sir Elfman. Is that a thing? Yo! And then we're gonna VIP Nick Vorsa too, despite Nick Vorsa not being here. Perfect. I was gonna be the three. I imagine it makes sense if we keep it limited, so that it doesn't become like a, like everyone's a VIP now. Um, Excellent. Well, Andrew, enjoy your new VIP status. You deserve it, brother. Yeah. All right. Um. So, so now that our Mac is 10 times more powerful. Wait, that's still so funny. I will never forget this moment. Okay. So it seems like the semicolon doesn't change anything, right? But if I do this, Ooh, error. Okay. It still takes like 3 seconds and so on, but I think it's fine. Um, great. Okay. Awesome. Next. Thank you. Next. Okay. Intro 2. Oh my god. Okay. To do. Fix the code to print hello world. Oh, so these are just the exercises. Like, they don't teach me anything. They just tell me, yeah, buddy, solve it. Okay, I guess I'll have to read the Rosai example then. I'm so confused. I guess also it's better if rather than the terminal here, I just run the thing, but inside the VS Code terminal. I think it was rustlings, and then I do like, what was it that I needed to do? Yeah, I just do rustlings. Okay, perfect. Okay, yeah, here's better. Wonder if problem with colors showing strangely was also power saving issue. No. Because I solved the colors thing. I solved the issue with colors, and you've seen it, right? You've seen that the colors are completely fine since like 2 weeks ago. That one I solved. To solve this one, you don't need to read external docs. Oh, okay. Symbol name exists. Oh, I see. So it's not print line, it's print len. Ooh, question. Huge question. Why was the compiler error saying this was a macro? It's a function, no? STD macros. What the hell? Huh? This macro uses the same syntax as format. Brother, what do you mean this macro? Oh, is this the thing where people are like, oh, print line is like 20 lines? Oh, no. Okay, that's fine. Let's go to next. Cannot find value x in the scope. You might have meant to introduce a new binding. Let x. Ooh, I see. So now let's run to the next exercise. Variables. So in variables we have this guy. So let x be equal to 5. Perfect. And I think that solves it, right? Yay! Okay, so we declare variables with let in Rust. That's great. Now, it seems like we let x, right? Type annotations need the type must implement. Oh, what? Type must be known at this point. Oh, we don't know the type yet. Right. Oh, I see. No, the type must implement partial equal. Okay. Consider giving x an explicit type. Oh. Help. Consider swapping the equality. Why would I swap the equality? Why is it Yoda typing? Okay. So then I imagine it's just I32. Imagine this is integer of 32 bits? Question mark? I think so, right? X is used here, but it isn't initialized. 42. Yo. Okay. Rust doesn't have function overloading. Rather. Why did you tell me that? And doesn't support passing arbitrary many params and functions. No. Oh no. So they need macro to make it work. No. Okay, that's fine. Sure. Damn, that's crazy. Okay. Well, this macro also does limited string interpolation, which regular strings can do. Okay. Okay, it was left uninitialized. This makes sense. And then it should work. Yay. We did it, people. Next. Eating flakes dry. Yeah, they're like it's because like they're crunchy and they taste very well, right? So, mm, okay. Let x be equal to 3. X is equal to 5. Oh, is it the immutability of Rust? Okay. Let mutable x be equal to 3. I kind of like this, no? I kind of like it. That the default is constants. Because then you're forced to know what things are going to change and what things don't. Interesting. Okay. Pretty good. Rust doesn't have no. Oh no. Okay. Just Sophie. Welcome to the chat. This is kind of rusty. Let's go with the pounds. Keep it coming. Okay. But yeah. What do we have here? We have an error and it says output number 3, number 5. Oh. Why does it say exercise done? Buddy, it's not done. Oh. And yeah, sorry. Mismatched types. Exercises that don't change this line expected due to this value. Let number. Okay, so it also has some sort of type inference where it's able to infer what the value should be. Okay. Or the type should be. Sure. Okay. Hehe. I love Rust. I hope you like it. Yo, we have the first Rust supporter in the chat. Everyone else in the chat was like, Rust is the worst thing ever. I hope I like it too. So this makes code more readable, so I like it. If you don't need to think about how value can change when reading, yeah, making it not default will make it so nobody uses const by default. Yeah, it's the same thing I was thinking. I heard Bob Ross. Team Rust here too. Yo, like Esther Enjoyer. Loves Rust. Oh, Penguin Operator, you love Rust? Damn, let's go. Okay, so we have more supporters than we actually thought. Okay, don't change this line. So we create a string, but then we have okay, a mismatched type. This is supposed to be a string, right? Okay, cannot add integer string. Fix the compiler error by changing the line below without renaming the variable. What? How am I supposed to do this? I mean, I learned Rust before Python or any other languages, so I'm kind of biased towards Rust. Interesting. Okay, so what's the problem here? Wait, what is the problem? Right? Why do we have a string and now we want to take a number? This just shouldn't be possible. Like, we shouldn't be able to do this. Just rename, yeah. Yeah, buddy. Fix the compiler error by changing the line below without renaming the variable. No, but what do we do? Let number. Oh, we're just using shadowing? Okay, I'm supposed to use shadowing. Okay, yeah, I see. Rust just handles everything I throw it, but I'm glad others like Rust. Somehow I find Rust easier and much enjoyable than JavaScript. Oh, for sure. But you need to go past the first steep, I think. This is shadowing. Yeah, okay. So just variable shadowing? Yeah, this sucks. Yeah, this one sucks. I do not like this feature from the language. This is really bad. Oh no. Well, yeah, we might consider quitting after this one. Like, oh no, this is really bad choice. Why? Why? Hmm. Why did they decide to do this? What could possibly be the motivation for this? Yeah, this sucks, bro. Yeah. TCI is to chat intelligence. Yeah, any Ross senior that can tell us, oh yeah, this makes total sense. I'm not gonna believe you either way, but I'm joking, buddy. I'm joking. If there is a Ross senior, don't feel offended. I mean, like, maybe there's an explanation, right? But it's. I mean, personally, I hate this. I hate the fact that we can do this. So yeah, this makes sense because it makes sense in the brain of someone who has this. All right, Zoe. So let's continue. Let's see. Okay, first thing we hate about Rust. First thing we loved about Rust, right immediately after, first thing we hate about it. So let's see. So you can rename, you can name every variable X for code obfuscation contests. Probably to be compatible with Python, where oops are applied. But with Rust rules, where the value to be shadowed is dropped. I So why would we want compatibility with Python? Like, and by that I mean there's like so many things that are just not Python oriented, like the Barrow checker or whatever, right? And like etc. That like why would you just want it to be compatible with Python? Just say like move on, right? You're learning a new language, buddy. Like why do why do you want to integrate Python here? I don't know. Because when you print it, the var consume and you can redeclare it again. Okay, so this will have to do with the var checker, I assume. Um, Maybe that's the reason, but I assume that you can just borrow it instead of doing that. Have you tried Python? Yes. Well, then you print on like 3 that var is gone from memory, and then again you can redeclare. Somebody confirm this, right? Oh yeah, maybe it has a deeper explanation. We'll see. Variable 6 to do, change the line below to fix the compiler error. Missing type of a const item. So I imagine this is just like int 32. Sorry, I32. Missing type. Yo, awesome. So now my question is, why do we have to declare const? Wasn't let? Okay, I imagine then that it depends on the scope. Like let is to define a variable in a given scope. Globally, you need to declare const. Okay, yeah, this is really bad. This is really confusing. Why? Okay, why is const not the default in this scenario, but in the other one it is? Probably devs become so tired at jobs where their fantasy of variable names is exhausted. var naming fatigue, I suspect it's caused by systematic overwork. Okay. Um, Forget what I said, it's totally wrong. Okay. In Rust, rule of thumb, everything is immutable, and only one can be owner at a time. If you want, borrow it, yeah, as reader. No writer. If write clone it multiply owner but shadow copy on stack or heap via bot. Buddy, you just mumbled you just mumbled a waterfall of words. I did not understand that message. I'm so sorry. Probably it's because many of the words I don't know what they are, right? Um yeah, yeah. But if as a rule of thumb everything is immutable, right? Why is const not the default here? But it is the default here. Let's see. Is listening to the voice of in function scope, compiler analyzes the entire function to figure out type of variable. But if it's global, it would need to analyze the whole program to figure its type. So they require no. Yes. Like the type makes sense. The constantness is what I'm talking about, right? Why is const not the default? Um, you know, like not the default outside of it. Oh no, I pressed the wrong number. No, cancel. Cancel the operation. Cancel the operation. Oh no. Abort. Abort. Okay, cancel. Yeah, there you go. All right, all right. You're saying const is compile time constant. Magic swim. Welcome to the chat, by the way. So, yes, like, sure. But that still doesn't answer the question. Why is const not the default? Like, am I supposed to just, like, is const. So, is there no such thing as a mutable thing outside of it? So, const is just not declaring the constantness, but just declaring that it's going to be a, um, a compile time variable. Rust is low level, as C, but merged with some scripting languages like Python and made to be comfortable to develop big low level projects. Yeah, wait, guys, I don't think any of this answers the cost question. Wait, why are we doing that? Right? It's like, well, let me check. Right here. Const defines via scope lifetime. Take a look at lifetime concept in Rust. Comfortable. Comfortable. And then the Kappa guy. Dude, that Kappa guy is my favorite. It's like such an uncomfortable expression. He's like smiling, but at the same time not. It's like so weird. Even if the stuff you're coding is so low level that your brain starts fatiguing, like lack of variable naming fantasy after a mental word, etc. Andrew says, no idea. Yeah, that is a great, like, right? Why? Why is const here not the default, but here it is the default? I would want it to be the default everywhere else. Anyways, I guess we'll learn about more things and then eventually we'll explain what happens. Functions! Yo! Let's see. Add some function with the name call me without arguments or a return value. Okay. So we create the function call me. Then we add it. That's it. Yo, let's go. We did it. Next. Okay, functions 2. Add the missing type of the argument none after the column. Okay. Let mute const. It's not really default. It's just different type of statement. So take a look at this block to get function scope lifetime. It will answer. We add prime a to tell Ross the returned reference. Lives as long as the input reference. Okay, so the thing is, we are going to learn this later, right? Lives as long as the input reference. Yeah, I mean, I'm not. I would have to. Like actually, understand these in the later lessons, so that we can then see. Oh, okay, that's the reason. So have me a little bit of patience. I think what Simply is saying, it's probably right the actual reason. Happy is cool. Sheesh. Hey, hello. So you're doing great. I spent a lot of time just to get the basics going. That's good. Chaz, we must help Cameron and Sharif learn Rust organizedly without spamming thoughts in order to keep learning curve organized. It'd be very easy if you understand how smart pointers work in C++. Yeah, no. Like, smart pointers make sense in C++, right? How does that explain my const thing? Like, because I'm not talking about const being used inside, like, the keyword const maybe inside of here, I don't know. I just mean it like, is const just another way to say compile time constant? It just doesn't refer to the constantness, because it just refers compile time constant, and that's it. I assume so, right? According to what I've been reading. But anyways, at the missing type of the argument after the colon, of course, I32 probably. Do we have I64? Do we have I16? Yes, I8. Ooh, we have all of them. 128. Do we have 256? No. Okay. Interesting. Excellent. Okay, next. right? So so far we haven't encountered one of the things that would make us be like, "Ooh, I don't understand what this is," right? So constants like define. Exactly. That's it. That's all I needed to know. Right? Root event told us like the thing. So is it like that? Oh, I think it's not true. Okay, yeah. Root event, buddy, what are you doing spreading misinformation? Yeah. Anyways. Um yes, compile time constant just bit deep. Run cargo build use real depth. It must be going in row data section of elf. Simlet, I'm so sorry. There's sometimes I don't understand what you're saying. I do understand what you're saying here, kind of. So yes, that's good to know. Andrew says, seems like const is really defined semantically from what is written here. Okay, yeah. Okay, that explains the question, right? Because you guys are like, oh no, the lifetime, right? And I'm like, brother, sure, but like, is it just hashtag define, right? Let's see, constant times. A constant item is an optionally named constant value which is not associated with a specific memory location in the program. Okay, so it's basically defined. Constants are essentially inlined wherever they are used, meaning that they are copied directly into the relevant context when used. This includes use of constants from external crates and non-copy types. References to the same constant are not necessarily guaranteed to refer to the same memory address. Okay. The constant declaration defines the constant value in the value namespace of the module or block where it is located. Constants must be explicitly typed. The time must have a static lifetime. Any references in the initializer must have static lifetimes. References in the type of the constant default to static lifetime. Okay, perfect. A reference to a constant will have static lifetime if the constant value is eligible for promotion. Otherwise, a temporary will be created. Yeah, this is too much yapping just to say that it's hashtag define. Okay, that's okay. By the way, don't take me seriously, right? Like, I'm saying all of these things, like, probably const has like another use, right? When I say this, like, it's like, I'm just joking. We just put 8. Yay, ring ring. The first time we spot a for loop. Damn, that's crazy. All right, functions for. So what is this guy doing? This store is having a sale where if the price is an even number, you get 10 Rust bucks off. But if it's an odd number, it's 3 Rust bucks off. Don't worry about the function bodies themselves. We are only interested in the signatures for now. Okay. Oh no. Oh no. Okay, this is really bad. This is really bad. Um, I don't think somebody will offend for trashing out. At the end, these are just tools. Oh yeah, but what I'm saying is I'm not trashing out. I'm not saying that it's useless. I sometimes just are like, oh yeah, this thing is useless, but like I actually don't mean it. Right. I'll say when I actually mean it, but yeah. Um brother, can ifs have parentheses? Please tell me they can. Okay, so I have the option to opt in. Okay, that's great. That's awesome. Never mind what I said then. Sell price, it should be an I-64 too. I imagine if I do I-32, it's gonna complain because it's gonna say like, yeah, okay. Perfect. Yippee. Okay. Functions 5. Fix the function. Fix the function body without changing the signature. Also, yeah. Oh shoot. Wait. N, then N. There you go. To do, fix the function body without changing the signature. So it's square. It returns this. Okay, let answer is square 3. So it's an I-32, blah, 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 blah. Expected I-32, found parentheses. Return. That's dumb. Okay, yeah. Sure. Perfect. N. All right. We transition now to the if. Damn, people, we're on fire. We're on fire. Okay, let's see. Um, where did he find these exercises? Uh, oh, wait. One thing I love is Rust makes you think and write safe code, which many garbage collected languages never care. And C has a lot of safe, yeah. John Black GG, where did he find these exercises? We found it on the Rustlinks website. Um, yeah, thank you, yay. That one is diabolical task. Yeah. Yeah, I think they meant for you to just remove the semicolon. What do you mean it would have worked, just remove the semicolon? Okay. So if I do this, wait, can I go to the previous one? Oh, I don't think I can go to the previous one. If I do this, right, will the compiler just accept it? Is it just a feature of a single line function? In which case I'd be kind of fine with it, although very... Oh my god, it does. Oh no. Dude, what? Genuinely, what is it? Huh? So if I don't include the semicolon, it's a return statement. If I do, then it's not a return statement. If I do return without a semicolon, will it be valid? Yes, apparently. Okay. Well, yeah. So one question. Will we have tools like linters and stuff that will allow us to just disable things like these? I can just say, please make sure that never in my code do I write a return statement as a non-semicolon statement. Will we have those tools? Andrew just said the most sacrilegious thing ever. Okay. Sounds. What are you eating? Sounds very crispy. Yeah, it's Frosted Flakes. Syntax sugar. Yeah, I mean, just remember this. Just remember this, buddy. Just remember this. Too much sugar, and you become a diabetic. Bars. I'm dropping straight bars right now. That's all I can say. That's gonna be my answer to that. I had the same reaction, but I got used to it. No. Rust is expression-based language. Last expression in a block is returned as a value. This is the sacrilegious thing I said. I said that Andrew had uttered. Yeah, this is just like I don't want to say it, but the Rust team deserves like a little visit, to their homes. You know, yeah, that's all I'm going to say. All right. Well, I don't like that, so I'm gonna code by my own rules. Return. Okay. Function bigger. Buddy, what are we doing? This is so funny. The last exercise was like, oh yeah, remove the semicolon, and he was like, write the entire function. It's like, optionally experiment. Do not mind this. And it's like, what? What are we doing? Okay. They have the inverse. They have the inverse. What do you mean they have the inverse? Clippy lints. Needless return. Checks for return statements at the... Do they not have the opposite of this? Do they only have this one? If so, I'm going to do things to them. I'm going to genuinely just do things to them. I don't know what to say, bro. This starts getting really crazy with din, box, and async frost. LOL. Okay, okay, let's see, let's see. Let's see. No idea what this is. It's okay. Bigger. To do, complete this function to return the bigger number. If both numbers are equal, any of them can be returned. Do not use another function call or additional variables. All right, thank you. So if A is smaller than B, then we return, this is the bigger one, right? So B. So I assume I'm just gonna change this and return A. Otherwise, return B. Unnecessary parentheses, buddy, who are you to tell me these are unnecessary? Who are you to tell me the parentheses are unnecessary? Oh no! I cannot believe they don't have parentheses in the ifs. Okay. Okay, I'll try to do it the idiomatic way. I imagine that the idiomatic way is just not putting parentheses. I'll try to comply. I'll try to comply. Okay? But just know, one day I'm gonna snap out of it. One day I'm gonna snap. It's not gonna be pretty. Um, let's see. Oh wait, they have it needless return, so it's fine. Implicit return. Oh, it's just not enabled by default. Okay. It's just a warning, you can ignore it. I know, but I don't like it when it has warnings. And I mean, it seems like the idiomatic way is without parentheses. Kind of like Go, right? So, I'm willing to do. Simply, no! No, simply! They're trying to teach us if statements. No! 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 No. That's a ternary operator, buddy. That's not an if statement. But yeah, could have done that for sure. Um, Picky eater. Fix the compiler error on this function. That's the error. I just spotted it. For this one. So what am I supposed to return? If food equals strawberry. Bro. Oh, sorry. Next. Expected string found integer. Yeah, so am I supposed to just change the value? Default disliked food. So it's supposed to express no thanks. Okay. Else. Ew. What happens if I do this? So am I supposed to just do no thanks? Stop trying to show off, bro. Neutral food. Huh? What is going on? Oh, so am I supposed to create if branches for every single... Oh no. Oh no. Okay, I imagine this is the else if statement, and then I can say if food is equal to potato, potato. Oh wait, no, potato doesn't have an E at the end. Potato, right? Potato, yeah. Potato. Then I return, I guess I can eat that. Dot. And finally we return no thanks. Yo, let's go. You can write it as match statement and it would be much more readable. Yeah, but they're trying to teach me the ifs. They're trying to teach me the ifs. So I'll go with the if. I'll try the match statement actually. Showing off in a lame way because Rust doesn't even have their name. Okay, okay. Whoa. Let's not bully each other. Let's not bully each other. Simply was showing us an alternative. Maybe it doesn't exist in the language, but that's okay. That's okay. All right. So let's deduce what a switch statement would look like. So I imagine it's switch. Oh, never mind. Well, match. Okay, match. So what am I matching, right? I would be matching food, I imagine. So then I need the keys. And I imagine here I have a case where I say, or actually, no in Rust, it's just going to be the string. Strawberry, and then 2 dots, and then they're going to make me return pois. I actually don't know. Let's see what the autocomplete gives us. Oh, damn. I had exactly written that. You could say I'm a genius. Strawberry. And then what do? I like need another set of keys. Do I need a colon? Okay, yeah. Yeah, no, let's wait until they teach us the match command. It's okay. All right. If 3. Yay. Next. Okay. Oh my god. Okay. Fix the compiler error in the statement below. Incompatible types. Expected integer found string. Expected I32. Okay, I imagine I can just return -1. Don't change the expression below. Identifier 1. Wait, what is the problem? If and else have incompatible types, expected floating point number, found integer. What? But you were not complaining before. Plus this thing returns a string. What are you saying? What are you saying, brother? So is it just this? Oh, I think the compiler error, actually the 2 is the one that has the mistake. Yeah, let's go. Yippee. All right. Also, simulates expression is equivalent to max AB. Thank you, Andrew. That's very helpful. Okay. Don't change the expression below. Okay, I think we passed with flying colors. Let's go. Next. Primitive types. Booleans. Okay. If it's morning, good morning. Define a Boolean variable with the name is evening before the if statement below. Okay. So then I imagine I just do, let this evening be equal to false. Can I just say not is morning? Yes, I can. That's great. Oh, what? It's still complaining. Hello? Why are we on calculate price of apples? Quiz 1? Oh, we have a quiz now. Oh, damn. Crazy. Guys, this is our first quiz. Okay. So that means I need to open the folder in a higher. Hello? Oh, okay. File, open folder. So I just open Rustlinks. There is no quiz. Oh, yeah, there is. Oh, shoot. I finished the Rustlinks program without knowing it. Okay. Quiz1.rust. Ooh, our first quiz, guys. All right, all right, all right. Who's ready? Uh, they take you back after the quiz. Okay. Oh shoot. You can click on the blue links in VS Code CLI. I'll open the file for you. Oh really? So if I close this. Oh, command click. Yeah, yeah. Oh, that's great. Wait, that's awesome. Hmm. Hmm. I would have done with a.maxb, much clean and max for production code maintenance. Yeah, true. True. Seambleed? Seambleed knows. No, Seambleed knows ball. Okay, so our first quiz. We're actually so brave that brother, let's start a timer. Timer. Timer has started. Timer has started, people. All right, this is a quiz for the following sections. Variables, functions. If Mary is buying an apple, the price of an apple is calculated as follows. An apple costs 2 rust bucks. However, if Mary buys more than 40 apples, the price of each apple in the entire order is reduced only to 1 rust buck. Write a function that calculates the price of an order of apples, given the quantity bought. So I'm supposed to... Okay. The function is calculate the price of apples, and then we're going to accept the amount that Mary bought. So amount... then I-32, and then we're gonna return back an I-32 that is the amount of rust bucks that she has to pay. So then, right, however, if Mary buys... Okay, so I imagine that if amount... Okay, I guess no parentheses. If amount is greater than 40, then I'm just gonna return... what was it? Yeah, whatever amount is. Otherwise, I just return amount times 2. Yay. Let's go. Excellent quiz. 1 minute, 10 seconds. Let's go. Okay, great. We surpassed our first quiz. Let's go to the next. Yay. Primitive types. All right, which I guess it's already done. Next. Next one is this guy. So we need to... Okay, now we deal with char. So note the single quotes. These are different from the double quotes you've been seeing around. Yes. So just like C. If my first initial dot is alphabetic, then we're going to print line alphabetical. Okay, numerical. Analogous to the example before, declare a variable called your character. Try a special character. Try a character from a different language than your own. Try an emoji. Oh, so you can do this in Rust. Interesting. Let char is equal to this thing. Oh, you can do this. That is interesting. Why would you ever want to do it this way? Question mark. So then, ooh, okay, so, ooh, this is, ooh, okay. Okay, I have so many questions now. In Rust, the char is 4 bytes. Oh, no. Okay. Well, it's because of Unicode code, but yeah, of course, right? Like, I understand the why, but like, why would you want to make such a choice, is what I mean. Does that... So then we're faced with a divergence, right? Does string in Rust mean a sequence of bytes, just like it does in Go? Or does it mean a sequence of characters? Right? Because it's not only the Unicode, like, you also have, UTF-8 probably. this theoretically can take only 2 to the 21 bits. We'll round it to the closest nice number of bits. 2 to the 21 bits? Oh, okay. I was like, well, this is not gonna be a great language. Okay, I imagine, okay, yeah. But so okay, I guess I'm curious now about strings. We'll see what the answer to that is. Create an array called A with at least 100 elements in it. Okay. Let A. Okay, I'm gonna guess how it goes. It should go something like this. No. Equals this guy. No. Okay, I hate this language now. Is it this? Oh no. Okay. Let's read what the compiler says. If I write that, will it give me a suggestion on what A should be? No. Okay. So if I do something like, oh, type annotations needed for, huh? Oh, okay. So I guess I specify the type and then I specify the length. Sorry, it's a semicolon. Hello? Or A is equal to this. Expected value found built-in type, so is it the other way around? Oh, what the hell? What? Wait, so am I supposed to do I-32 this, and then the other thing? Wait, it's so confusing. Wait. Okay, let A, right? Then to declare the type, I do this, and then just say I-32 100 elements. And then initializes them all to 0. Oh, it's not initialized, so if I just do this, I'm getting really tired. How to create an array in Rust? Well, actually, I guess I can just go to the Rust by example, whatever something book. Here, types, conversion, modules. Can I just look up something? Array. An array is a collection of objects of the same type stored in contiguous memory. Arrays are created using brackets, and their length, which is known at compile time, is part of their type signature. Dude, yeah. Wait, that's exactly what I have here. Okay. How to initialize it? Slices are similar to arrays, but their length is not known at compile time. Instead, a slice is a two-word object. The first word is a pointer to the data. The second word is the length of the slice. The word size is the same as usize, determined by the processor architecture. Okay. I like the fact that we have slices. I like that. I feel that's pretty nice. Okay, so yeah, this is indeed the way. Oh, you do it like this. Initialize with 0, 500 elements. Not sure how much I like that. I kind of do, I kind of don't. Okay. Okay. Huh, real, I did not know that. Know what? Return size of A. Huh? Huh? What? Wait, Andrew, what did you not know? What? Is this 4 bytes? Am I tripping? Wait, what? Read my last message. Oh, root event. Okay. Okay. Oh, wait. I haven't been reading the chat. That's the reason. Okay. Strings, on the other hand, are UTF-8 encoded. So if you write only ASCII, you will get 1 byte per char. Okay, sure. Root event. In C, A is an int, which is also 4 bytes most of the time. After A for the type, yes. A being 4 bytes and not 1. Oh, okay. It's only if I declare it as let A be equal to... Oh, sorry. This is not... Char C is equal to A. What's the size of C? Okay, I see. So it's only when you specify the type that it actually changes it. Interesting. Okay. Great. Exercise done. Whee! Continue. Primitive types. Okay, part 4. Yum. Get a slice called nice slice out of the array A so that the test passes. Okay. So imagine that if I just do nice slice, and then I'm going to say this is going to be how do I declare a slice? What a good question. Let's see. Fixed size array. Yes. Then a slice. Okay. Empty array. Example of an empty slice. Yeah, so how do I create a slice? um, yes, this is an array, right? But how do I... Yeah, let's do what Lancaster is saying. Take a look at the understanding ownership slices, other slices sections of the Rust book. Okay, let's go there. Give me 1 second. I'll be back. Oh my. Oh no. 10%. Okay, let me put in the other one. Let this one charge it. The slice type. Slices let you reference a contiguous sequence of elements in a collection. A slice is a kind of reference that does not have ownership. Okay. I want to know the syntax because Rustlinks will eventually teach me. Oh, so I just write this. I imagine, of course, this has to do with some sort of the borrowing model and etc. But for now, I'm going to follow the Rustlinks thing, right? So let's say A, and then I say 0 through 2. Excellent. Oh, they want me to pick a specific slice. Okay. Great. Oh, what? Oh, it's not inclusive? Oh, I don't know how much I like that. I don't know how much I like that. It's okay. I feel I can live with this, yeah. Destructure the cat tuple in one statement so that the println works. Okay. Let something something equal cat. So the way I imagine this could work would be in this way, where I just decompose, saying name, age. This is a very nice feature. I like this. I like this. Right. If I remember correctly, you can dot equals, but I'm not sure. Where did you previously use inclusive ranges? Oh, I haven't previously used inclusive ranges. It's just that the syntax itself just seems to be more. To me, it's more legible if it's inclusive, right? Because it's like, the start and the end are both included. Because that's exactly what I see, right? If I see 3, I imagine, oh, position 3 is included, right? It's easier to think that way, it seems to me. That's why I said, like, oh no, I can live with this because like either is fine, right? You get used to it. Use the tuple index to access the second element of numbers. So let's second, and I imagine it's numbers 1. No. Okay. 1. Oh, okay, that's good. Dot 1. Okay. I see. So what is the difference between arrays and tuples in Rust? And of course, arrays and tuples are different, right? Tuples in, say, languages like Python are immutable, while arrays are mutable. But right, but then in Rust, if I have an array like let array, and then I just declare it to be like a I32 of 0 elements, I haven't declared this as mutable. So this is also not possible that I change it, right? So what would be the need for a tuple? Well, get used to half open ones because they are superior. For example, A, B, B, C gives you a range from A through C. Also, yeah. For sure, for sure. Tuple can have elements of different type. Okay. That explains it all. Perfect. Next. Yay, primitive types, we completed it. Let's take a look at vectors now. Oh my god, there's so many, bro. Oh no. Oh no, can we? All right. It's 1:43 p.m. Let's do the next section on vectors and then take a break of around 1 hour because I need to eat lunch. And then after that, we can continue. Okay. It's Georgie. Why Rust? Well, just because. You know, as we just wanted to learn Rust. Yeah, we wanted to learn Rust. All right, let's see. Array and vector. Oh, so they're different. They're different things? Okay, what does this, what? Use the vector macro. Brother, what does this mean? The vector macro? Do I just call vector and then like, oh, vec? Ooh, it's orange. Oh no. And then I pass in A. Mismatch expected a struct vec I32. Found struct vec I32 4. Can you save the video on YouTube? I save all of the videos on YouTube. It is saved on Twitch, but it only lasts 7 days on Twitch, and then it gets deleted permanently. So, yeah. Alright, I guess we're gonna have to look for vectors now. Vector. Vector. Creating a new vector. The first collection type we'll look at is vect, also known as vector. Vectors allow you to store more than one value in a single data structure that puts all the values next to each other in memory. Allow you to store more than one value in a single data structure that puts all the values next to each other in memory. That's an array too. So it's just the difference in methods. Maybe this guy allows for pushback or something like that. Okay, vec new function. Now that we added a type annotation here, because we aren't inserting any values into this vector, well, it doesn't know what kind of elements we intend to store. Rarely need to do this type annotation. Rust conveniently provides the vec macro, which will create a new vector that holds the values you give it. Oh, wait. So we did this right? Let vec maybe A. Do I just force the type upon this guy? Huh? Brother, what is this? Where are we? How am I? What? Am I just supposed to not use parentheses? And then I just get that? Okay, yeah, no. Well, what am I supposed to do then? Mismatch types expected what I32 found integer and 4. Yes, yes, brother, that's what I want. Please. Okay, curly bit, curly braces maybe? Bro, let's read the compiler. Expected at I32 found an integer. How do I create a vector from an already existing array? This guy is doing this, and this guy is an array. You just need to copy the values. I don't want to copy the values. Wait, how do I? Wait, how to initialize vector in Rust from already existing array? There you go. Yes, yes, exactly. This thing, this thing. Even from, it can be created from an array by using the from method or the into method. What the heck? Hmm. Okay. Okay. So do I just do vector to that's from? Hello? Oh, vec. From, and a. I know it asked me to use the macro, but screw them. I'm not gonna use the macro. There you go. I code Rust in my own terms. Okay, vec2. We'll see. It says thousands of warnings. Okay, what do we need to do now? An example of collecting a sorry. An example of collecting a vector after a mapping. We map each element of the input slice to its value plus 1. If the input is 1, 2, 3, the output is 2, 3, 4. What is this? What? Here we also want to multiply each element in the input slice by 2, but with iterator mapping instead of manually pushing into an empty vector. See the example in the function vecmac example above. What? Each element in the input slice by 2 and push it to the output vector? Wait. An example of collecting a vector after mapping. We map each element of the input slice to its value plus 1. If the input is 1, 2, 3, the output is 2, 3, 4. Right? Try writing. Oh, I see. No, sorry. So when we call input, what are we doing? Oh no, our single line functions this way. Our lambdas written like this. Dude, this is awful. One of the things I do have to give to JavaScript is this syntax makes like so much more sense. Oh wait, is that allowed? No. Okay. Okay, so what are we doing here? Collecting a vector after mapping. So what does collect just create a copy of the vector? Wait, does what? What is this? Like input.iter.map for each element plus 1 and then dot collect. What does that even mean? What is this example? This is the most confusing thing ever. Does any of you understand this? What am I supposed to do? First of all, what the hell is this line? I understand what it's doing, but why do we need to do it this way? Why wouldn't this thing dot map suffice? Right? This is like link Q in C sharp. Yeah, I don't know C sharp, so I have no idea. So what are we doing the dot collect? Check the return type of map. Okay, yeah, that's a great idea. Constrict. Okay, pub and map, and then returns a map, self, and then F. Takes a closure and creates an iterator, which calls that closure at each element. Map transforms one iterator into another by means of its argument, something that implements F and mut. It produces a new iterator, which calls this closure in each element of the original iterator. If you're good at thinking in types, you can think of map like this. If you have an iterator that gives you elements of some type A, and you want an iterator of some type B, you can use map, passing a closure that takes an A and returns a B. Okay. Map is lazy. It is best used when you're already working with other iterators. If you're doing some sort of looping for a side effect, it's considered more automatic to use for than map. Wouldn't this be really inefficient though? Because you'd be copying all the elements over to a new array, right? Do you know about iterators? Like not in Rust, which is another problem. So I mean, I can do exactly what they asked me to do, right? Like solving the exercise is not the issue. It's like really understanding what it is that, you know, what are the things related to Rust, what it is that motivates them. Multiply each element in the input slice by 2 and push it to the output vector. So they just want me to have both output.push, great, push in the element. Yay. Oh, something failed. What is it? Multiply each element in the input slice by 2 and push it to the output vector. What am I doing? Like, I'm doing exactly just that now. This argument has type I32. Consider dereferencing the borrow asterisk. What? Okay, I think Rustlinks is not teaching me the things in the order it should. Because it should have taught me what this is before even letting me do it. It should have taught me about, like, borrowing and all of that before even introducing this exercise. Or maybe I'm just dumb. Yeah, no. Okay, I think it should have just told me that. Oh wait, there are readmes all the time. Oh, never mind. Well, all right, guys. All right. That was a good, entertaining first session in Rust. Let's take a 1 hour break. It's 2 p.m. already. I need to eat lunch. And then after that, we can continue learning. Okay? So see you guys in like, yeah, it's a Rusty session. I agree, Penguin Operator. Yeah, let's come back at 3 p.m. PST. I'm going to turn off the stream and then turn it back on so that you guys get the notification that it started again. But just know, 1 hour from now. Okay? If you're not following, that's a great reason to follow so that it can notify you that you should come back. And yeah, I'll eat lunch. You guys should eat whatever you guys want and should go out and stretch, stand up and move and all of that and etc. Yeah. All right. I'll see you guys in 1 hour. Okay, 1 hour, 1 hour. Remember, 1 hour. All right, 3 p.m. PST. 3 p.m. PST. Come back. Have a good lunch to Lancaster, or I imagine dinner for you, or something like that. Um, you should get affiliate, man. It won't affect immigration. It does, actually. It does. It's really unfortunate. Um, yeah. Anyways, I'll see you guys. I'll see you. Whee! All right, let me stop the stream. And 1 hour from now.